Hello, good afternoon. Welcome in Budapest on behalf of the project, our MSO4SC project, Mathematical Modeling, Simulation, Optimization for Societal Challenges with Scientific Computing. I'm very glad that we gathered together here to our first scientific workshop. I hope that during the workshop we'll have more other such scientific workshops. And before telling some words about some technical details, I let Javi to tell you some words.
Yeah, I also want to welcome you. Thank you all for your presence here. As you know, what we wanted to do with this workshop is to share with you the things we are doing right now. We also want to know from other people external to the project working on scientific topics to let us know the kind of things you do and the kind of needs you may have related to infrastructure. And then we will also try to gather some feedback, trying to be, let's say, a bit fun, with some funny, not being too boring. So basically that's all from my side. I hope you will enjoy this workshop. I hope that we all will learn each other. And I'll leave the floor to the first talk from Zoltán. Thank you.
Thank you. And before starting the first talk, just about the general organization of the workshop, let me ask the work package leaders and those guys who organized the session, please be the chairman of that session. So after this session, there will be a session about the work package 3 results. I'd like to ask Carlos and Javi to chair that session, and please ask people to upload in the break the presentations. And so on. For tomorrow, the earlier section, Adgir, I'd like to ask you chair that session, and then Christophe, and then Marcus. Marcus will be here for tomorrow for the first session, and then again Christophe, and so on to Wednesday. It's clear the rule. You can see the SSID and password for the Wi-Fi over there. MSO4SC is protected for the upstreaming, and hope you will enjoy this experiment. In the sense that we broadcast it to YouTube, and we have also the possibility to have questions through the air, on air. Let's see who will be the first who will ask us after in the discussion part. Let me tell you first now about this story, the history of this project, and this starts with the MSO technology. Most probably you all know the MSO concept and technology. I will give you a short example about the MSO technology, maybe not to you, but for somebody who is listening this broadcast and not familiar with this MSO technology. And EU Medicine, our network, basic network, EU Medicine, and how EU Medicine organized this MSO4SC project. So the MSO is an abbreviation for the mathematical modeling, simulation, and optimization. This is a key technology in the most sectors of the industry. We all know. The M is for mathematical modeling. Modeling translates a challenge of the real life into a mathematical problem, and also provides an algorithm for the solution. And if we have already an algorithm which will approximate the mathematical challenge, then we shall have an implementation on a computer to make a simulation. The simulation implements the algorithm which is coming from the mathematical methods, and in the simulation we run this algorithm on computers and evaluate the results. We can show a lot of details more from the simulations, if it is properly set, than from many experiments. So here the evaluates we can compute some indicators, we can generate some maps, so visualize the results. And the optimization finds the best design, roughly speaking. This MSO technology is a close interaction with data processing. So a lot of time we are provided also not only the problem but also measurements. And these data processing, sometimes they are called digital twins, the MSO and the data processing has to be handled together, and the computing part, the simulation part, is often connected to HPC, high performance computing. Let me show you one example, and the part of this example is also pilot of this project, of the MSO4SC project. The challenge is that the nitrogen oxides level is rather high in several cities. So people suffer from fresh air, and policymaker asked whether it can be organized so the traffic or some other parameters so that the NOx concentration became smaller. And they can measure it, but proper measurement stations are very expensive, and only few can be put to a city. And therefore, modeling and simulation of this system is natural. So here on the map, you can see a part of the city of Győr of 130,000 inhabitants, and also you can see already after the simulation of the wind flow and also the concentration. And you can see a red spot area here, where the average, where the concentration of the NOx is much, much higher than the average. And up to now, the policy is set to the average. And people living very close to the maximum suffer a lot from this high concentration of the NOx. So we need some simulation tool because with measurements, all the hotspots cannot be measured. With simulation, we try to capture all of them. And for that, we set up a simulation and optimization framework and with some databases for the traffic and the meteorology and the city databases. We set up a simulation method, simulation part, which needs pre-processing, and then if it is already prepared, the simulation, we set up the initial conditions for the design parameters, which are traffic signal parameters. We simulate the traffic, then the emission, and after the emission, the dispersion. If you need accurate dispersion, then you need big computers or good softwares. And this was done by a commercial software. And this simulation was verified. Some pictures from the typical work for the mathematical modeling, simulation, and optimization, modeling the geometry, meshing, fitting the two components of the simulation together, the traffic geometry and the mesh computational mesh of the airflow. We have meteorology data, and from all of these, we can compose the simulation in the city. And we get the results from the simulations, the hotspot areas, and we can compute the indicators. This coupling of the simulation and optimization is a very straightforward coupling. More sophisticated techniques can be used as well. For example, model order reduction techniques, or using some other tools from the so-called digital twins methods, from data processing and also from the simulation. In general, the algorithms, we have to notice one point here. In general, the algorithms develop much faster than hardware. So it's not enough to say that if we want to have a more efficient computation, then we have to get a better computer, buy a better computer. It is already proved in many areas of the science and technology that in particular in that case, which is projected some numbers about that, that for linear optimization, it was measured that on a rather long period, it was measured the algorithm development and also the hardware development. And during those years, LP, linear programming solvers, the solver algorithm has been very improved 303,000 times. And the softwares and the hardware has been developed 1,600 times. So in total, these bring the multiplication of these numbers, give actually the speed up of LP solvers on new, that time new hardware and with new algorithms. And this shows that 1 minute calculation, 1 second calculation at the oldest time was, after the development of the software and the hardware both, 1 minute in the new time was 2 months in the old time. But to achieve that great achievement, we need also the algorithm part to be developed. EU medicine, it is in the industry, it is recognized that mathematics brings a lot of improvement in simulations and in the innovation, but it is not reflected back enough in the policymakers level. Therefore, mathematicians established the EU medicine, the European Service Network of Mathematics in Industry and Innovations, and this is a network of network. The national networks, you can see the countries belonging to this network on the map, and these national networks represent the entire community in those countries they are from, and this is becoming a big network with mission leverage the impact of mathematics on innovations and to be a dedicated one-stop shop for mathematical services, and to be able to provide a dedicated one-stop shop for the industry. We have to build an infrastructure for the mathematical services. So this is the point where our project started. We had in EU medicine, we had a wish to generate an e-infrastructure, and there was a call, and EU medicine composed a consortium from us, here represented from a research group represented here in the workshop, and with experts ATOS and HPC expert ATOS, and we made a consortium for this, for building this infrastructure. So to build a HPC-oriented cloud infrastructure, from HPC, it has a large compute power. From cloud means that we can reach this infrastructure simply, roughly speaking, and to put there advanced mathematical tools, mathematical development frameworks, and also end-user applications for solving societal challenges. And in this workshop, we are to provide information what has been already done in the project, and we would like to introduce these frameworks, the infrastructure, and also the end-user applications in the workshop. This was an introduction of the main framework of the project, and I'd like to ask Javi Nieto to give his lecture. He would like to.
I was told it's on the website.
Yes.
Oriol, it's here.
So I'm the project coordinator of MSO4SC, and I wanted to tell you a few words about the project in order to let you understand the purpose and the things we want to do. So first of all, some words about maths and computation. I was attending last week an important event related to HPC in Barcelona. It was the European HPC Summit Week, and there was some session related to mathematics and the HPC world, mainly, in which ETP for HPC, which is the main platform for HPC research in Europe, was telling about the ideas of the next research agenda, in which they wanted to incorporate somehow mathematics. And they were talking about several topics in which mathematics could help. For example, they were talking about extreme scalability, how to scale with data analytics, how to improve data placement and movement. And basically, what they had in mind is how to use mathematics in order to improve the things that we need to do in computation, scheduling algorithms, these kind of things. But here the question would be, and what about the things that the computation world can do for the mathematics world? This is one of the things that we are trying to answer from MSO4SC. We see that there are several things that in which we could support the mathematical people, such as research on new numerical methods, support more efficient execution of the software that you are doing from the mathematics point of view, and also to understand the kind of resources you may need. Also supporting co-design with the computation people. Also, we know that benchmarks are important for you, so you want to compare different mathematical methods for solving the same problem, these kind of things. And MSO4SC can support in order to solve some of these questions. Basically, what we had in mind when we started MSO, or when we were thinking about the MSO4SC proposal, was that it was necessary to facilitate the way in which modeling, simulation and optimization applications are deployed, are developed, are designed, and of course in which they are run. On the other hand, we were aware that of course you have HPC, but also now it's possible to get access to cloud resources which are rather efficient. Not as much as HPC, but still it can be exploited. Also we wanted to understand how we can support the execution management of the applications which are based on some mathematical frameworks. And here is where MSO4SC comes up, and basically what we wanted to do is to bring together three main pillars. One of them was the computation part with HPC and cloud infrastructures. Then we were bringing math application development frameworks in which mathematics are the central topic of this software. And then we needed to validate and demonstrate the things that were possible to be done with some pilot applications using the mathematical frameworks. And in this case, very related to the current scientific challenges. So basically, what the main objective we have with MSO4SC is, as you can read there, to design, build, test, and deliver an infrastructure for hosting this advanced mathematical software, and to support all these applications using them by using HPC and cloud computing. So yes, in order to provide a very high-level view of the different layers we identified in MSO4SC, we have on one side the hardware layer. Let's say we have cloud, we have HPC. In the case of no, this one. Okay. In the case of cloud, we have the typical providers because cloud is always more commercial. You have Amazon, you have Microsoft Azure. While on the other hand, you have more academic world related to HPC with some infrastructures such as Prace. You have EGI, people who are providing really efficient resources, but still it's not so easy to access to these infrastructures. So somehow we wanted to be able to use both of them, extract the best thing of both of them, and for doing so, we included some layer on top of that, in which we will provide some orchestration algorithm which enables the possibility to really use both HPC and cloud, especially for applications which are modular enough. So we assume that some parts, of course, require HPC because of the efficiency and the network latency, these kind of things. But still there are other parts that can be run on cloud efficiently enough. And this orchestration will merge both of them. On the other hand, we also needed some monitoring in order to retrieve what's going on with applications, what's going on with the infrastructure as well, in order to solve issues if necessary. And then we have what we call the application development layer, in which we have the mathematical frameworks. Of course, we have in this project three of them, which is Phoenix, Field++, and OPM. And also we wanted to provide some MSO portal in which any stakeholder would be able to find all the tools they need. For example, pre- and post-processing tools, easy to integrate with their applications, a marketplace for publishing the things they were doing, or just to take something which is already published there for being used. Also visualization tools, these kind of things. And then the last layer would be the one of the end-user applications, in which we have some applications which are using the tools we provide. They are using the mathematical frameworks we provide, and of course, in a transparent way, they are using all the infrastructure. So basically, in the end, what we want to do is to provide some services to the scientific, to the scientists in different domains. Basically, we have three main parts. One of them is the one related to HPC and cloud infrastructure. With this orchestration algorithm I was mentioning before, with this infrastructure monitoring and also the applications monitoring, which we are working this month as well, and on provision this part of the HPC and cloud resources, facilitating the access to these technologies. On the other hand, we have the part of the MSO portal, in which, as I mentioned, we will have several services and tools available for stakeholders, software and data management tools, the marketplace visualization pre and post processing, also some software for facilitating simulations management. Then from the mathematical perspective, as I mentioned before, we'll provide some versions ready to be used of Phoenix Field++ and OPM, customized to the infrastructure we're providing, and with very nice packaging, so it will be very easy to use them. And finally, we will also provide the possibility to use the pilot applications that we have in the project. We have the list there, mainly as 3D urban quality, quality prediction, I2Brain, Happy Magnet, Sieve Affinity, OpenFlow. So these are all the things that we expect to provide to all of you and to any people from the scientific world, in order to facilitate the access to the mathematics-based technology, enabling math as a service model from the infrastructure. And that's basically all. Thank you. So you have some question now, or then we go to the next one, is the introduction of the work packages, right? So Carlos. So I leave the floor to Carlos from CESGA.
Thank you, Javi.
Okay, wait for
it's going to be very fast. So.
No, just to
We still need the sound. Okay.
So first of all, thank you for Zoltán for the organization of the workshop, and also to Javier Nieto, of course, and to all of your team for bringing us the opportunity to meet here in Budapest. That's a lovely city I personally didn't knew before. It's amazing. I invite, if you still didn't have time to visit the city center, it's really beautiful. Lovely. Thank you very much. So I'm going to give just a very fast presentation or overview of the WP3 activity, because today we are going to focus mainly on the WP3 presentation. So we are going to have a lot of information about the activity that we are developing in the scope of this work package, and also on the future activities of this work package. So I'm going to be really fast, because I'm going to talk after the refreshment again about this. So in WP3 we are working on the cloud technology, and as Javier Nieto mentioned it, what we are trying to develop is the connection between the bottom of this slide, the infrastructure layer. We have there the machines, the hardware, and so on, and the top of this slide, that is the developers and also the final users. So what we have found is that we need to work hard on the connection between the developers and the software that you are developing, to be able to move this software fast to the hardware. So you can take the opportunity to scale your software in fast supercomputers, but also on the cloud, very, very fast. So we're mainly working on the infrastructure layer, providing the cloud technology, also working in the monitoring, not only on the monitoring of the infrastructure, but also on the monitoring of the applications, to provide useful information to the final users about how the simulations are going on, if the application is running good, if it is producing really good results, or if something is failing. Then we have our Orchestrator, that is a piece of software that will be able to complete all the steps in the simulation process, including pre-processing of the data, the simulation, and also the post-processing of the data. It's like a kind of workflow manager. And then we will be also developing a portal in which not only for the users to submit the simulations to the infrastructure, but we will integrate other tools in this portal that will be very useful. In principle, for example, for the software developers to publish new versions of the software that you are developing, to make them available faster to the final users, and to the users to select the different software that they want to use directly from the portal, and to use this software directly also in the available infrastructures. Right now we are providing a supercomputer to the project, that is the Finisterrae, but we are also using a cluster from STA for testing of the technologies, and we will be incorporating an ATOS infrastructure in the project. But the aim and the scope of the project is to incorporate new infrastructures so they can be easily used for the software using this, the cloud technology that we are developing. Very easily to incorporate your own resources. For example, if you have some local cluster in your premises, to use this local cluster, but also in connection with other European infrastructure, like for example the Prace infrastructures or the EGI infrastructures in Europe. I will not talk more about the activities of WP3 because we are going to have whole sessions during the day. So that's all from my part. Thank you. WP5. If you have questions on WP3, for example, we are going to have all the afternoon to talk about that.
Okay, we're not going to hustle a bit. As you can see, I'm not a PowerPoint expert. Okay. There is a special key. Hello, I'm Christophe Prud'homme. I'm a professor at the University of Strasbourg in applied mathematics, and I'm in charge of WP4. This is the work package for the mathematical frameworks. That is Phoenix, OPM, and Fil++. So basically the underlying workhorse of the pilot application that we are going to run in the project. So the objective here is to be able to define the different specifications that will be required of the mathematical framework in order to run in the cloud. But we'll see later today how it is designed, I mean the cloud framework, and we'll then develop the various changes in the mathematical framework in order to run this. But however, I will discuss a little bit some aspect of the change that might be required or not, because I think the three frameworks have already a lot of ingredients in them in terms of architecture, usability, packaging, and deployment. But I would like to mention something which is a big trend in scientific computing, at least, or for many software actually, but type of software. You want your scientific software to be automated, as much automated as possible. You want it to be scalable. You want it to be integrable. You want it to be capable. What does it mean, capable? It means that you want to be able to do all different kind of operation. Like you don't only want to solve a problem like fluid flow, but you want also to optimize, to be able to optimize in an automated way, or rather automated way, the flow around some objects or around a structure, like an airplane, for example. You would like to incorporate advanced analysis, for example, in your software. So you want to integrate new features that help engineers, researchers to make the right decision. Integrable, what does it mean? It means now, as actually Zoltán showed, in the simulation system, you have a large set of tools with a chain that is actually run. So you need your different pieces, and often which are requiring large simulation, to be linked together and integrated into another piece of software. So your software needs to be flexible enough to be integrated in complex chains. I will mention tomorrow, for example, a pipeline that we develop in medical science, and where we are integrating various software in a rather complex chain. And scalable, of course, because you want to be able to take advantage of high-performance computing. So we want this, definitely. So here we talk about these three mathematical frameworks. This is what we are going to develop, and they are the basis of different application that will be run within the pilots. So what is, I'm going to make some teaser slides for the different mathematical framework. They will be shown tomorrow and on Wednesday. So Fil++, it's, so we develop Fil++ in Strasbourg mainly, but we have also various partners and collaborators for this development. So it's a C++ mathematical framework that allows for a large set of Galerkin methods from finite element, spectral element, or reduced basis methods. It supports an advanced language, so mathematical, basically to write your mathematical formulation within C++ to ease the programming. And it scales on a large number of processors. It uses well-known frameworks like PET-C and SLEP-C, but we develop also homemade preconditioners for very large-scale problems where we can actually sometimes be actually better than those guys in some situations. And in order to automate as much as possible, we provide toolboxes which are allowed to easily set up mono or multi-physics applications, and to create new ones thanks to the mathematical language. It's easy to add a new toolbox. And lastly, we have also, and that could be interesting for MSO4SC, I think for the discussion, because we have also enabled reduced order methods, which allows for real-time simulation. That is, you have your very large simulation, which is parameterized, and you would like to reduce the number of degrees of freedom. So we have methodologies for that. And then the solve time would be like in orders of magnitude smaller than with the initial system, like say infinite element. So that could be also interesting to look at this as a next step eventually for MSO4SC to integrate in this framework. So this will be discussed on Wednesday. Regarding Phoenix, so Phoenix is all about automation. It also provides, like in Fil++, the language for developing nicely, very close to the mathematics, or like the mathematics, say, your problem. And based on, say, the variational formulation, you have automatic generation of the software. Also the mesh, this is from what I understood from what Johan sent me. So, because here, what you see here is actually a mesh which is generated automatically from the problem definition, and I think here is like after a few adaptations. So it will be presented on Wednesday, and you will see how they can produce this kind of simulation from rather nice definition of the problem. Very nice definition of the problem. They include also automated optimization, which is an extremely powerful framework in order to actually do this kind of simulation. And of course, they scale. If we want to present, OPM is about flows in porous media. So basically, it's not basic actually, it's flow in a reservoir simulation. It provides various toolbox in order to tackle a wide range of simulation. And you have access here to various benchmark data, and it seems full cases. But I'm sure Javier will present that on tomorrow in detail, what will be available. And they have, so this is, I guess, the REST Insight software in order to do the visualization of the porous media flows. So if I go back now to the different thematic, to the different aspect of the work package, in terms of software architecture, what do we want? We want a building process which is rather standard. I think all our framework follows the same process, which is good. We use all MPI. Maybe some of us also are also multi-threaded, allow multi-threads within MPI. We use tools, or we share some of pre-processing tools, like, for example, with Phoenix or with Fil++ Salome, which is software developed in France for to do the full simulation chain from pre-processing to post-processing. Gmesh, of course. And regarding post-processing, I don't know if REST Insight is based on ParaView, or this is Insight, or this is your own software. This is your own software.
It's open source.
It's open source software, okay. But ParaView is also used by Fil++ and Phoenix, so we share this. And within the project, we'll have also ParaView Web, the web interface for ParaView, in order to visualize our results. There are also some in situ capabilities. Actually, it should be here in co-processing with ParaView, which allows to interact with the simulation directly. So actually, we share a lot of things between the various frameworks, I think. There are, of course, differences. And some of the major developments will be probably in the monitoring and of our framework, so that the cloud people can actually understand what is going on, and either in terms of performance, debugging, or just interact with the simulation, perhaps. In terms of usability, documentation will be an important point. The mathematical frameworks eventually have their own documentation set, but we propose also to have some tools in order to generate nice technical documentation from the specification that we develop here. So for example, we set up, so this is the current address. I hope it will become book MSO4SC.eu, but I'm sure it will be done soon. So this is a recent discussion about being able to deploy easily technical discussion on a website directly. So for the deliverables, but also the specs, some codes, some examples, benchmark specifications, things like that. You can access this. There are other examples of this kind of technology. We use it for Fil++. If you look at book.filpp.org, you will see what we have done with this. There is another aspect here in order to be able to go to not only to provide pilots or simple modification of or just parameterization of the pilots. We would like to be able to allow the user to develop new applications. And here scriptability plays an important role. Phoenix definitely has this capability. For OPM and Fil++, this is not so the case. However, there is a nice project at CERN, which is a Kling interpreter. It's basically a C++ interpreter. So you take your C++ code, and this is interpreted by Kling. So you have scripting capabilities for free using Kling. However, there are some performance issues that needs to be tackled. And there will be, of course, access to shared scripting if we cannot have scripting a la Python or using Kling. Packaging. We have been working a lot on packaging. Each framework will be able to present their achievements on this, but regarding standard Linux packages, I think it's helpful to have those because it's easy for users or external users to be able to access the software. I don't know the stage at which all the frameworks are in this area, but we can probably discuss that tomorrow and on Wednesday. And there is this container system, container technology, which is very nice to be able to deploy applications. So initially we started with Docker. However, there are some issues, like if you want to deploy Docker on a cluster, usually the engineers are not happy regarding the security. And so we move also towards the solution of Singularity, which is developed at Lawrence Livermore, and which provide a nice secure environment for the clusters. And also as shown in benchmarks that actually Docker also provides very nice performance, and Docker and Singularity provides extremely nice performance with respect to parallel computing. So, and the idea is that we want to be able to run application in a very simply. So the first command, this is just an example. I'm not saying like it will be exactly like that, but basically here, thanks to Docker, for example, you can just retrieve the software with this command, the Docker pull, and Docker run. You just run. Well, it's a tad more complicated than that, but it boils down to this in order to run the applications. So it should be as easy as possible to run the pilots and the applications. This is an example of what we have done in Fil++. So we store on Docker Cloud. This is a free, there is a free repository here where you can upload your Docker images, and you have access here to various Docker images. If you are interested, you can also pay for private repositories if you don't want to expose some of your work. This extremely powerful framework. And the last part is about deployment. So in that case, that would be through MSO4SC. Docker Cloud, actually, that I just shown you a screenshot of the Docker Cloud web page. Docker allows to deploy services. They have here, you see, they have all kind of tools to deploy services, but not necessarily to do high-performance computing or to deploy big applications. So here we are going to use the MSO4SC infrastructure, and Javier Carnero will present the entire pipeline, which should look like this, with 4 main stages, where you start here from the MSO portal to the deployment on the compute nodes, running the simulation, making sure that everything is all right, and then visualization here. So that's what we are going to discuss this afternoon, right? Well, there is the last bit. This is like, you know, the mandatory deliverables. So we have to deliver one soon, actually, on the mathematical framework, following the discussions on WP2 and WP3 regarding the infrastructure. What does it mean for our mathematical frameworks? What we need to do? So we need to deliver this very soon. But I think in general, we are looking good in terms of what we provide so far in terms of build and runtime environments. And then, in the second stage, we'll need to provide where we stand regarding the implementation of what we did. So thank you for your attention, and that's it.
Okay, so my name is Johan Hoffman, and I'm the work package lead for work package 5, and that is about the pilots with the end user applications. So first, the objectives is then to demonstrate and showcase the capability of this infrastructure, and that will be done in terms of a set of pilots. Most of them build on one of the 3 mathematical development frameworks, and then there are a few pilots outside that. And this work package is about first defining these pilots, and then to provision the infrastructure needed, and then implement the pilots. And this will be done in 2 iterations. So the deliverables represent 2 such cycles. So first defining and defining the pilots, and also an evaluation strategy. then to bring about infrastructure, basically integrating the results of work package 2 and work package 3, and then implement the pilots on top of that. And then we end each cycle with an evaluation report. And this is the protocol that we will follow, which is based on verifying the needs identified in work package 2. And we will do this in 2 steps. The first one verifying a TRL level of 7, and then a TRL level 8. And basically the difference is that on TRL level 8, the end user should be able to run these pilots on their own. So all these pilots will have dedicated time during Tuesday and Wednesday, so I will not go into too much detail, but I will show a teaser of the different pilots. So as mentioned, there are 4 different groups. There are the Phoenix pilots, the Field++ pilots, the OPM, and then 2 pilots which are outside this. Also, there are already being indications of additional pilots to be added. That will be also discussed on Tuesday and Wednesday. So, starting with one of the Phoenix pilots, the floating wind turbine. Here, the context is the design of floating wind turbines with the focus on the floating platforms. So the pilot will function as a design tool for virtual design of such platforms. And for each pilot, we also define test cases. And test cases will function in this first iteration of the pilots as an evaluation criterion to verify that the pilot is performing the way we expect. So in this case, there are 2 test cases. One is derived from the Nautilus platform, which is an established benchmark where we have experimental results, and then one general basic benchmark called the marine benchmark, which is used in the scientific community, where the focus is the free surface flow. Another Phoenix pilot is the CFD dispersion, and this will also function as a subroutine for the 3D air pollution or air quality prediction pilot. Basically, this is a computational fluid dynamics pilot together with the dispersion module. And to evaluate the performance of this pilot, we have chosen an urban street canyon problem. This is identified here as this is the 42nd Street in New York, and to the right you see a model version of that, which there are detailed controlled experiments that we can use to verify this pilot. Moving on to the Field++ pilot, we have the Hi-Fi magnet. And the context of this is that this is used to develop the existing and to design the next generation of high field magnets. And this is in particular in a collaboration with the LNCMI. And this is a multi-physics problem, and one of the main demands is the actual coupling of the multi-physics. And that becomes even more elaborate in the I2 Brain pilot, another Field++ pilot, where also data is integrated from various modalities. And the goal is here to model the function of the eye, certain functions of the human eye, with the purpose to draw conclusions of brain functions or early indicators to detect neurodegenerative diseases. The OPM flow application is dedicated to model very complex porous media flow, where with realistic geometries and including also different wells and the connection of these. And this is also a very complex coupled problem, including some specific features like automatic differentiation, which distinguish this from the other pilots. SIB Affinity is a pilot with focus on the pharmaceutical companies. So the goal is to be able to predict likelihoods of bindings of potential drug molecules. And finally, as was described by Zoltán before, is the 3D air quality prediction pilot. And here the goal is to connect models of the traffic, which then function as an emission source in an urban environment, and based on meteorological data, solve the computational fluid dynamics problem and draw conclusions about various hotspots of pollution. And this could be used both as a monitoring or forecasting system, but also potentially as an urban planning tool. So that's the basic set of pilots that we defined in the proposal, and which we will use in the first round of verification for the project. Thank you.
So thank you very much for the introductory talks. I encourage people, in particular the stakeholders, to join our workshop and ask questions, because this is devoted for the user request gathering, and we are very glad to hear stakeholders' information, stakeholders already present or later coming. Just one technical question, because we are already in the break, and I know that some food is waiting for us outside, that we have two rooms for the workshop. This is the lecture room, and there is one room for the consultation with stakeholders or for internal consultations. This is the Tobac one. This is the name of the room. There are indicating arrows for that room too, or I can show you. There are already which is a good news, there are some special companies who requested some particular time for our one of our partner for the OPM guys. Just there will be reserved sessions also, but there will be open consultation possibilities also there. So thank you very much for this early first session, and please enjoy the food in the break.
Gratuito. Jó, de webprezenterúzó megy a hang, és mégis ugyanaz a probléma, mint ami nálad volt. Rajta.
presentations. The next one is about the features of the infrastructure. And Carlos is going to present this part. He's working in the Galician Supercomputing Center, CESGA, and he's the leader of workpackages 3. So,
thank you, Javier. So this is the schema of this WP3 session. We'll be talking about the infrastructure. Mainly the objective is to provide the infrastructure to be a tool to the developers to provide solutions to the final users, instead of being the opposite way, instead of being a kind of pain on how to use that. So I will start with the functionalities that we plan to develop in this infrastructure. So I will talk a little bit about the MSO process development, how the applications, from my point of view, are being developed and then used by the final users and also by the developers. In this case, it's the case of mathematicians, but it happens also with physical applications or chemistry. You are also usually developing your software and your algorithms using your own local resources, typical your PCs, Macs, and local clusters that you have for your own. Typically, you don't develop software using supercomputers because it will be very time-consuming, probably. And then you realize that you need to use a more powerful system because maybe you are using more elaborated models, or you are trying to produce better results. So you need to have access to more hardware resources. I'm talking about typically memory, but also about cores or processors or more powerful storage system. So then you try to move your software, your developments from your local resources to a more powerful system, a supercomputer or a cluster that you have to get these additional resources. And in this process, there appear a lot of problems. I am talking about some of the problems that can appear, but probably you know about many more. Usually you have not lack of knowledge, because probably you have already used other HPC infrastructures in the past, but maybe you lack about knowledge about how specifically this system is configured, what versions of the libraries they are installed in this system, in this HPC or in this cloud, what operating system is installed and how it should be used. And in the other side, probably from the part of the infrastructure provider, there is no staff dedicated to support you and to understand your problem, your applications. Probably they can answer some specific questions like what is the version of the MPI library and things like that, but they will not have probably the time to talk with you to understand what your application is doing and how is the best way to run the application on this infrastructure, or to install the full stack of dependencies of libraries that you need to run your software. Also, in this kind of systems, there is a very tight software ecosystem that is very difficult to change. We have, for example, in our case, in the Finisterre, we have an operating system, and for us it's very difficult to move from the actual version of the operating system to a newer version, even if you really need for that, because it's a production system and it takes a lot of time. And it's not only the case of CESGA or Finisterre resources, but it's the typical case in many production infrastructures, of course. But in the case that you are able to finally install your software, that probably it will take weeks or even months. I think that Victor or Javier or other can tell about the experience trying to install the software in the Finisterre infrastructure. It has taken a lot of time. You can maybe you realize that you have a newer version of your software because you want to improve continuously what you are doing, what you are developing. You have new functionalities. You have maybe solved some bugs or improved the way that it is working. So when you have finally the software installed in the system, you have a new version, and you have to start again with the whole process. So this is a very time-consuming process, and usually when you are willing to use the HPC infrastructure, you are very close. You have some let's say, limited time because you want to produce results very quickly. So at the end, the solution is like, okay, we are not going to do that in that way. I'm going to use my local resources, or you get more memory for your PCs or whatever infrastructure you are already using. So in principle, the objective, or what we are willing to develop, is the capacity to move transparently and effortless all the software stack that you are already working with in your laptops, in your PCs, to develop the softwares, move this software stack from your local resources to the HPC and cloud resources. This is what we want to do, without having to recompile and install all the dependencies and all the things, so that you, the developers, can maintain the control of all the software stack that is going to be used in your applications in the remote infrastructure, in the supercomputer. And how we think that we can achieve this? We think that using the containerization technology, we will be able to move the containers from your PCs, where you have the control of all your software stack, to the supercomputers. This will maintain all the software stack, all the dependencies, or the libraries to the versions that you really want to use, and so we will not have any kind of conflict with the infrastructure, with the supercomputers, dependencies and libraries, and we will have the power of using more processors, more memory, faster network connections and storage system. To solve or to achieve these objectives, we are going to face some challenges. I mean, usually it's not as easy as say, okay, we are going to use containerization and it's going to work. We don't need anything else. No, we have to test which container technology. Christophe has already talked a little bit, because there are different technologies to implement containerization. We started using Docker, and this implied a challenge for the kernel that we already have in UNISTRA, for example. Then we moved to UDocker, and it has some limits about the performance with MPI applications, that this might change in the future, but actually it is not a good solution. This is what we have found so far. And now we are moving to Singularity, and the results are being very, very promising. And Tamás is going to talk a little bit about that. The results achieved about the performance of the applications, of real applications. I mean, not just benchmarks and synthetic applications, but about the actual applications that we are going to, or we plan to deploy in our infrastructure. We have to also support the use of this technology in our infrastructure, in the UNISTRA, in the ST cluster, in the ATOS cluster, and so on, and to analyze what is the best way to do this deployment of the containerization. We have to integrate the containers technology with the batch system that we are using, with the operating system, and also in the whole chain of operations of the people that is working, the staff that are maintaining the system, to understand and to provide support on this new technology, because until now we were not using containers in supercomputers. Also we have to determine which are going to be the performance difference between using a native compilation of the software and using the containerization. What is the penalty? And also Tamás is going to talk a lot about this and what he has found regarding the performance. So the objective is to design the mechanism to optimize this process and measure what is the performance loss, if there is any kind of performance loss, compared to the standard way that we have been deploying software in HPC systems until now. In this way, we will be able to streamline the development or the deployment of this software in HPC and cloud infrastructure. It will be what we could call the software cloudification, or provide software as a service. Once we are able to achieve the first objective, we will be able, or we would like to provide a marketplace of containers, what we are calling in the project a product catalog. It will be in some way a place in where the developers will be able to to put new versions of the software, and the users will be able to get these versions of the software, these different versions of the software, and to try the software directly through the portal that we are using. This is the other piece of software that we are developing. The portal that will be the connection between the developers and the final users of the applications. Other functionalities that we are planning to deploy is the capacity to deal with workflows or pipelines that, as Christophe explained it before, to get a real solution to a problem, you need different steps in the simulations. And with the Orchestrator, we are going to be able to do some kind of workflows or pipelines in the whole process. So at the end, we'll be able to orchestrate all the resources from the point of view of the HPC and cloud resources, but also integrate interactive visualization in the process to provide a complete MSO workflow, including pre and post-processing, data movement, and the pulverization of the resource achieved so far. In some way, it will be also a kind of marketing tool for developers to provide or to show what are the results of the software that you are developing, providing the results that have been achieved so far in the portal. And of course, the portal will be, we expect to be very easy to use for the final user. Other tools will be also integrated in the portal, like the data management for moving data between different tools, to provide a kind of community support to the final users, to provide support in the usage of the applications, and also to be able to access the documentation of the software that you are developing, for example. So finally, in some way, MSO4SC will be a kind of interface, an interface between the infrastructure providers, HPC or cloud providers, and the mathematical development frameworks that we find here, and will be able to be in the middle of both of them. The development frameworks will be also providing new software applications or final user applications in different scientific or industrial areas. And the project or the frameworks that we are developing will be in the middle of both of these worlds, between the infrastructure and the software developers. In some way, will provide an integrative platform for the different scientific communities to develop and exploit the software, the knowledge, and the simulation results. With the results that are achieved in this process, we will be able to know a little more about how to optimize the software that you are developing. So with this optimization, new versions of the software with improved results will be developed and available in the catalog, in the marketplace, and this will close in some way the development circle. Also, we plan to incorporate other existing infrastructure, like I mentioned, Prace, EGI, UDAT, in this framework, so they will be able to provide resources to the developers and to the final users. It will be, or we aim to be, a tool for opening these existing infrastructures to some communities that are actually not users of these services. Some of the required functionalities that we have detected with the help of the developers and some final users, and probably we have to include more of them. These functionalities are based on the questionnaires that on the answers of the questionnaires that we collected at the very beginning of the project. And we mapped the answers of these questionnaires with requirements, and then these requirements to the functionalities that we need to implement in the infrastructure. We also need, or we are also asking for additional functionalities that you are missing in the ones that we plan to implement. And for that, Javier Nieto is going to introduce the innovation game at the end of this session, or maybe tomorrow, so we can detect or collect more functionalities to be implemented in the framework. Some of the functionalities are especially the fast and easy software deployment to reduce the cycle for the development and the usage of the applications in cloud and HPC infrastructures. We will also need an authorization mechanism, so we can certificate that the final users are the ones that are really using the infrastructure and have access to the data and to the software. We will implement this software catalog that we have been also already discussing and talking about. It will be a kind of marketplace including different software and different versions of the software, so the users can decide which software they want to use or test and which version of this software they really want to use. We need a data management tool to be able to move data from the, for example, from the user premises to the cloud, and then produce results that will be stored in the cloud, and maybe the final user will want to download this data to their local resource, to their local PCs, for example, so to be able to download this data to the system. Also, we aim to support the execution of multiple simultaneous simulations with hundreds or even thousands of cores simultaneously. For that, we need the support of supercomputer systems, not only cloud resources, to support tight and loosely coupled models, because some of your applications really need, for example, InfiniBand networks with very low latency. We need the support for the workflow, for pipelines, so at least some not very complex pipelines, but we'll check if what we are implementing is good enough. Also for input-output data management and movement of the data, and very important, the pre- and post-processing capabilities, including remote visualization of the data that is produced. Also, it was detected that it's very important for the user to be able to interact with the simulation while it is running, to be able to, for example, to change parameters while the simulation is running, or to cancel or stop the simulation if the results that have been achieved so far are not very good, for example. So, and for that, it's also very important to monitor how the simulation is progressing. What are the results that are achieving? That if everything is going okay, or if there is any kind of issue, so they can cancel the simulation and start again with different parameters, for example. And also, it's been detected that it's very important not only to use cloud and HPC resources remotely, but if you already have your own local resources, to incorporate this infrastructure to the computation or to the simulation. For example, for confidentiality or for security reasons, you don't want your data to be moved outside of your premises, and for that we will be able to run the whole simulation without moving the data outside of your site. And for example, if you want to also use fast prototyping or using your local resources, etc. So what have we achieved, or what have been working so far during this already 6 months of the project? Well, from the WP3 point of view, that we are mainly, we know more about the infrastructure, about the HPC, about the cloud. We wanted to analyze the MSO software to know how it has to be run, what are the dependencies, and so on. For that, we put in principle, 2 infrastructure available to the developers, the Finisterrae and the SC cluster, and installed all the mathematical development frameworks in these 2 infrastructures, and started with marking the codes and checking the dependencies and how to run all of them. And then we produced also a containerization version of this software. In some cases, there was already a containerized version of the software available, but in other cases we had to develop or, let's say, integrate a container for some of the frameworks. And we started comparing the performance results of using containerization and the native compilation. And we Although in the first part, at the beginning, we found some performance problems when using UDocker. With the Singularity, we have detected that the performance is going really, really good. We have to experiment more when using, for example, hundreds of cores, if the performance is also scaling well with the number of resources in the system. But we are very optimistic, actually, about the performance that we are going to achieve. And also, 3 of the pilots are almost ready in this infrastructure, and we plan to also develop the containers of these pilots to check about the performance and how to run all of them. So we have been producing pilot and prototyping of different solutions and different technologies. And we have identified the technologies for this fast deployment in the clouds and SPC, but also for the final users. If they want to use PCs, for example, the containerization can be very, very useful if we want to do fast deployment. We have demonstrated some results about the performance, and Tamás is going to present some of them later. And also we will have a presentation from Victor about deploying containers in this infrastructure and with an increased number of cores. We have demonstrated the use of remote visualization integrated in a web portal, and how these results can be orchestrated. That is going to be the presentation from Javier Carnero from ATOS, how to orchestrate the different parts of the simulations. We have identified technologies for producing the catalog of the software, a marketplace. We are in discussion about the monitoring of the applications and the infrastructure. The infrastructure part is, we know very well about that, and the part of the applications have to be is an ongoing discussion with the software developers. Some demonstrations could be shown in the following sessions. Still a lot of work is pending, of course. We have almost 17 months left, so we have a lot of work to do, but we have tested and produced some proof of concepts very important. About the monitoring is something that is going on. We want to do not only monitoring, but also that this monitoring is intelligent and very useful, producing added value to the final user. So it can provide not only informative data, but also predictive and correct information to the final user, to know about the status of the infrastructure, what are the resources available, and about the simulations, about how the simulations are running, if they are already running, or they are pending, or they have finalized, and how the simulation is progressing, and how much is the estimated time to finish the simulation. So we had to work on the proofs. I have to finish, I know. I am almost ready. On the proofs to get the information that we want to collect, how to manage the log that are producing the applications, and how to store all this information, and process all of this information in a way to produce very useful information for the final users, and to be able to provide some kind of monitoring dashboard. This is, for example, a monitoring dashboard that we are using actually for the Spanish Port Authority, that they are running daily simulations in the Finisterra infrastructure. For them to know, for them and for also for us, for the maintenance of the infrastructure, it's very important to know if everything is going okay, or there has been an issue in the running of the simulation. Sorry, but because it is in English, but I think that you will understand that the red colors means that something is failing. And the green colors means that some of the simulations have been run correctly. And then you see not only that they failed or worked correctly, but also some, let's say, results about how much time it took the different steps of the simulations, and how everything went about the simulation. So our intention is to produce a kind of dashboard to the different softwares about how the simulations were going on for the final users. So in the next presentations, and this is my last slide, sorry, we'll have an overview of the portal in the infrastructure orchestrator, including a complete demonstration of these technologies, about the use of the base technologies to support the fast deployment of the software using containerization, and a complete workflow of the MSO process, including remote visualization on HPC infrastructure. Also, we'll have some results of performance on the containerizations and on the Prace services that are available to the users thanks to Oriol. And that's all from my time. Thank you. I'm sorry for this that time. No questions, or do we have time for questions?
First of all, we do Javier's presentation, and then
okay.
we leave some time for questions.
Thank you.
Okay.
Okay. Vamos a su PC, ¿no?
So the next talk is made by Javier Carnero from the Advanced Parallel Computing Laboratory in ATOS Research and Innovation, and it will be about the orchestration and the portal we are preparing in the context of MSO4SC.
Okay, wait a second. I'm trying to set the Okay, so in this presentation I'd like to show you how we're going to access to the features of the project, of the platform of the project. In this way, I'm going to show you the three main components of the architecture, which are the MSO portal, the monitoring, and the orchestrator. Okay, so about the portal, it's going to be the main entry point of the end user, of all the human users. We want to be, of course, user-friendly, and it's going to be composed of different services, which the most important are a software marketplace, in which we will be able to see all the different applications and all the different mathematical frameworks that we can use that are already in the system. Also a data catalog in which we're going to be able to browse or surf between different data, not only input data, but also output from the different simulations. This part is going to depend on the application that they want to publish their data or not, of course. We're going to have pre and post operations with a graphical interface embedded in the portal. So we will be able to see the outputs and the inputs, and also perform different operations over them. Of course, we are also be able to execute the simulations or the applications. We will be able to monitor the infrastructure and the executions. So we will be able to see how the HPCs and the virtual machines are working, and also the applications that are running. We will be able to see if the execution is going well, is going bad. We'll be able to stop them, change its parameters, and well, interact with the simulations. And finally, we'll have some learning tools, tutorials, question and answer tools. Also, we will integrate probably the tutorial or the documentation that it's been doing in the work package 4 and 5. Okay, this is the high-level architecture of the portal. I won't be very technical. Just for you to know, we'll have an authentication and authorization component, which will allow us to use different organizations or different communities inside the portal. So let's say, for example, if you're working with petrol, maybe the data you publish, maybe you want that everyone has access to it and things like that. We'll have the front end, which is going to be the main landing page of every user. And as I said, it's going to be connected with different components of the data catalog, as I said, a visualization tool to visualize the data, also connected with pre-post processing tools, marketplace, the monitoring, and the experiments management tool. As you can see, the portal is going to be connected with the monitoring and the orchestrator. Okay, as we just started with the development of the portal, I'm going to show you some pictures in order to give you a whole picture of how the portal is going to work. This would be the marketplace. In this case, every organization will have access to a catalog of software resources. In this case, I've put Phoenix, Field++ as an OPM of mathematical frameworks. And also the floating wind turbine. Okay, from this we will be able to choose the components that we are going to work with or that we are going to provide to our own organizations inside the portal. Okay. Well, it will going to have the typical features of a marketplace. We can charge for some of the features if we want. We will also have other different features as, for example, ratings, comments over the software, things like that. Well, and also, once we acquire a software for our organization, we're going to be able to use them, selecting, I will be talking about that a bit later, selecting them to run the mathematical frameworks or the applications, and also register our own applications. For example, if we have Field++, but we are developing an application using Field++, where we will be able to register here, okay, inside the organization. About the data catalog, we will be using CECAN, which is a component of FileWare. The data repository is designed in a way that, for example, well, this is an example of OPM. In this case, what we want is not to copy every different repositories of every people into a common repository of us. Instead, we're having a catalog which is going to be connected with the different actual repositories of the different partners or the different users of the application. With this catalog, we will be able to register our data. We will be able to tag the data, so then we can search, we can filter this data, we can put metadata or useful information of this data to use it then in the simulations. And well, license, it's using the DCAT format. Well, it has these features. We can talk about that later if you are interested. About the experiments tool or the experiments management tool, it's going to be the part of the portal that actually is going to run the simulations. As Christophe said, this is going to be the workflow operation or a high-level workflow. Firstly, we will select the software we are going to use. We will select the data from the catalog that we want to use as an input, and also we'll select the different inputs depending of the application. For example, in Phoenix, you could select the number of iterations you're going to run, for example. Then this is going to be sent to the orchestrator and the monitoring part, and what it's going to do here is to deploy the execution. In that way, for example, well, if we have an application, we are going to copy the data from the repository to the HPC. Maybe, for example, we have the application in GitHub and we need to build the application in the infrastructure, or copy executables or binaries from other parts. We want, for example, to create virtual machines. For example, if we want to run different things in a cloud environment. While we have this and all the deployment has been done, we're going to run the simulation. Okay, in this part, the orchestrator is going to be working with the monitor to take smart decisions on, for example, how a specific job or a specific part of the application has to be run. For example, let's say we have 3 HPCs and one of them has a high load in that moment. For whatever reason, the orchestrator can decide to put this job in another HPC or things like that. It's going to communicate with the monitor, and it's going to allow human interaction. The monitor is going to be showing this information in the portal, and a human or the end user is going to be able to stop the simulation or rerun it in a different way, or interact, okay, with the simulation. And finally, when the simulation is finished, we'll be able to check the results, check logs, executions, data information, the outputs, everything, okay? Also, the outputs will be published in the data catalog we said before. In this workflow, there is not pre and post operations, but of course, we will be able to do it. So before select a data input, for example, we'll be able to do a pre-processing in the portal, also with the data generated. Okay, this is something similar as what Carlos showed you before. This is going to be how the monitoring part in the portal is going to be shown. It's using Grafana. In this way, each organization or each application in an organization, it's going to be able to have its own dashboards on how or their monitoring. For example, let's say an application, it's going to have some specific metrics that it's not going to be in other application, or for example, for some end user, a metric is going to be more important than for other user. So users is going to be able to build different dashboards to see actually what is happening with the simulation, okay? Well, also we're going to be able to have alerts. Let's say a simulation runs during 5 days. If you don't want to be in the computer all the time, or anything happens or something like that, the end user is going to be capable of creating alerts for their simulations. For example, let's say, the infrastructure, let's say an HPC, it's offline for a while. you can put an alert or some specific metric of a simulation. You can set a threshold and say, for example, send me an email if these thresholds, things like that. Well, this is just the same as the alert manager, just to show the alerts is going to be presented in the portal, of course. Okay, about the pre and post processing in the portal, we will be using different tools. In this case, this is ParaView. In a way, we will be integrating web tools. For example, ParaView has a web version. And also we're going to use virtual desktops or remote desktop integrated into the portal in order to perform this application. So instead of have to install this application in your computer, copy the data and things like that, you will be able to run it directly in the portal, selecting the data. Okay, this is another example. Velocity. Okay, about the learning tools, basically we are planning to have two of them. One is AskBot, which is this. It's like a Stack Overflow, Stack Exchange, things like that. The user will have karma. They're going to be administrator users or expert users. The idea here is to have a dynamic place in which end users or new users could, or for example developers of applications using the mathematical frameworks will or can ask questions and be answered quickly and also publish for others to check. In the same way, we're planning to use Moodle as an academy inside the portal, something like that, in which we will have tutorials. I don't know, we can have courses if we want, different universities or things like that. It's very flexible. I imagine you already know it. If you have questions about this, you can, okay. Okay, that's all for the portal part. Well, this is a lot of, I think I'm saying a lot of different things. I don't know we have, if you have a question. If not, I'm passing, okay, to Orchestrator. Okay, in this part, if you remember the original architecture, this is the lower or low behind the portal layer. In this case, we'll have the orchestrator and the monitoring. This layer is going to actually run the simulations and check what is happening, okay? The orchestrator is going to deploy and execute the simulations, and as I said, it's going to execute it smartly somehow. About the monitor, is going to provide information to two ways. One is going to be the orchestrator, and the other to the portal, okay, to the humans. This would be a more technical architecture, just to show you, well, how all of things is going to work. The portal, when we select the data and we select the software and things like that, it's going to, it's going to produce a blueprint, okay, of the execution, which is a TOSCA file. I'll explain this a little bit more. This TOSCA file is going to be received by the orchestrator, and the orchestrator is going to first do the deployment into the infrastructure, which is going to be different HPCs and also different cloud providers, and also it's going to be connected with the monitor to check measures first from the infrastructure and also of the executions. The monitor is going to be connected directly with the infrastructure to know what is happening, And mostly that is all. As you can see, the monitor is also reporting to the portal, so the end user is going to be able to send again different blueprints while the orchestrator is running in order to change the simulations. This something is not already designed, but we have to decide how exactly the user are going to interact with the simulation, but it's something we plan to do, okay? This is the same I told. Okay, so all of this is really nice, but at the end, how the mathematical frameworks are modeled or introduced in the system, and how the applications are introduced in the system. If you are a newcomer in this project and you have an application, how could you integrate in our system? Well, as I said, we are using Tosca. Tosca is a description language. Maybe you know it. It's similar. Well, it's a Jan language. It's similar to JSON and things like that. It's very simple, and we are not extending, but we are creating verbs or words in this language in order to easily model the different application or the different mathematical frameworks in the system. In that way, the mathematical frameworks will be modeled using Tosca, the applications, and also the inputs. As I said, these are text files. In order to have a more graphical way to develop this modeling, we're planning to use Alim4Cloud, which is an open source tool, which is going to, well, it allows us to draw the application with boxes and things like that, and then Alim4Cloud is going to traduce it into text files. Okay, and also Alim4Cloud it will be integrated in the portal. Okay, I'd like to show you some examples of these Tosca files in order to show you how different things can be modeled in the system, and these things will be then used by the orchestrator and the monitoring part. In this case, this is the Tosca file, and this is the graphical view of this Tosca file. We have FT2 node, which is representing an HPC. In this case, it's representing the Finisterrae infrastructure, and inside it we have another node which is called single job. As you can see in the Tosca file, we have FT2 node, which is of type HPC nodes compute, and we have the single job, which is from type HPC nodes job. This is the language we are developing using Tosca in order for end user or developers of application to use it to model their application. In this case, well, I think it's clear. All the infrastructure things are going to be of type compute, and all the different tasks or the different components of a model are going to be jobs. As you can see, for example, we can set here different inputs. In this case, I'm putting the credentials of the HPC in order to connect and talk to it. And in the job, I'm going to put the jobs option. For example, here I'm telling him that we are using srun. As you can see here, I said that the HPC is a slurm type. It's using the workload slurm. So these are the typical inputs of a jobs. For example, let's say we are not using a slurm and we are using another one. We could still have this kind of options, and the orchestrator is going to actually run it in the different workloads. Also, we have the relationships important. In here, we said that this job is going to be contained in an HPC, and the HPC is FT2, for example. I want to show you this. Okay, I'm connected here to the Finisterre 2. As you can see, I don't have right now any jobs, and I want to show you how the orchestrator. Well, something I haven't told you. Right now, the monitoring part, as we are developing it, I'm not able to show you it right now because it's not connected with the orchestrator. In this sense, right now the orchestrator is doing itself simple monitoring in order to the orchestrator to be able to work, okay? Okay, I've made a little script in order to be easier to show you this demo. What I've done right now is to send single blueprint, which is what we saw before, to the orchestrator. This is going to be done when we register a new application in the marketplace, okay? I want to show you now this is the web interface of the orchestrator. Okay, as you can see right now, well, this is not going to be shown in the portal, but just so you know, the orchestrator right now is aware of the blueprint single job. Okay. This, as I said, this is what. Okay. This. Okay, so let's say we have already this single job application in the marketplace, it's acquired, and now we want to do a deployment. To do a deployment, what I'm doing here is to pass to this blueprint, I'm going to pass it different inputs. In this case, I'm passing the inputs of the Finisterre 2, yeah. And so I think mostly that, okay? If we see right now in the deployments, I have here this deployment, this is the topology of the deployment, okay? As we can see, we just created a deployment, but this deployment is not deployed or is not installed in the HPC. Right now, we are only telling the orchestrator that this is the deployment we want to do. Okay. Next thing I want to do is, well, as you can say, anything happened yet in the HPC. Right now, I'm going to create the deployment. What's doing here is in the Tosca file, I haven't put any deployment mechanism. So right now, it's not doing really anything. If I had put it, for example, a deployment script, I could have deployed anything here. For example, let's say a script that builds some software, copy something from here to there, etc. Things like that. In this way, I'm not doing nothing because I'm just running an srun command. Okay. Here in the website, we can see that the orchestrator, okay, already deployed or installed the deployment into the HPC. And finally, I'm running the jobs. I have a deployment, the deployment is installed in the HPC, and now I'm telling him, okay, the single job, now you have to run it. Here it's queuing the HPC job. It's connecting to the login node of the Finisterre. The task just started, and task succeeded. Right now, the orchestrator is monitoring the HPC. If we see here, the Finisterre 2, now we have a job that is completed. It's very quick. and the orchestrator in this case just finished, okay? It has monitored the single job and just is telling us that the task finished, okay? That will be the workflow of an execution. Of course, all of this I'm doing from an script. At the end, that's will be doing by the portal, okay? Now I want to show you a more complex example. Oops, this is not. Okay. Okay, this is a more realistic example. In here, you are telling, using the Tosca file, that we're going to have finished array as infrastructure, and inside it we are going to run 4 jobs, which 2 of them are going to run in parallel, okay? Let's say, for example, the first jobs could be, I don't know, well, different things, okay? This is the Tosca file. Probably you don't see it very well. We have, well, the finished array is not here, but we have 4 jobs. And if we can see, we have, for example, the first job, which is, all of them are of type HPC nodes. I have the first job is of type SBatch, of Slurm. I say is contained on the FT2 node. I have the second and third parallel jobs, which have 2 relationships. One is that is contained in the FT2 node. I'm telling the orchestrator that it has to be run in that HPC, and also I'm saying that depends on first job. The same for the third job, and the fourth job is depending on the third and the second. Again, if I run it, here I'm uploading the blueprint. This is something that's going to be done the first time we put an application in the portal. Then I'm setting the inputs here. Okay, deployment is created. Now I'm installing the deployment. Again, in this case, the deployment is doing nothing because I haven't put any script about deployment. As you can see, the deployment is following the same structure or the same graph. First is going to do the operation of the finished array 2, then the first job, then second and third, and finally the fourth here. As you can see, we have here only the completed job, and now I'm going to run this dummy simulation. Okay. You can check that the orchestrator just started the first job inside the HPC. If we go here, we have a new job, okay, which is first job in cola corta, which is pending right now. Hopefully this is going to be quick enough. Okay, as you can see in the orchestrator, well, you don't see it, but it's doing the monitoring right now, okay? It's checking, in this case it's 30 seconds, it's checking the status of the job, and if the job is finished or completed, it's going to run the second and third in parallel inside the HPC. Let's wait a second. Okay, it's completed. Let's see. Okay, the task has finished, okay, and now it's running third parallel job and second parallel job, okay, it's running it. If we see in the orchestrator, okay, we have here 2 new jobs, third and second, okay. While this is still running, I want to show you maybe the most interesting example. Okay, so those were dummy examples in order to show you how the orchestrator works and how these Tosca files works. In this case, I want to show you how we could model with Tosca a mathematical framework and then an application using this mathematical framework. I showed you before what is called node templates in the Tosca language. In this case, to model a mathematical framework, instead of templates, we are going to use types, node types. So I'm saying here, I'm going to have one job, which I'm calling it Phoenix iter, which means an iteration of Phoenix. And it's going to be derived from HPC nodes jobs, so I'm telling the orchestrator that this is a job. As a properties, I'm going to set it that it's going to have iter number, to say it's the first, the second, the third, etc. And also, I'm going to put here some jobs option. For example, in this case, I'm saying that this jobs is always using this command. Also, I'm putting here another type of job for Phoenix, which is called Phoenix post, to do post-processing of Phoenix. In this case, I'm telling him that it's also a job. It has iter number to do the post-processing on the proper iteration. It's going to have a file, so which file I want to do actually the post-processing, and also the job option. In this case, I'm using here the same command. So this could be the mathematical framework model in the portal, model using this Tosca file. If we are developing an application, for example this one, in this application I have two iterations of Phoenix, and I have already acquired Phoenix, and I have these models, okay? So I'm saying, okay, this is my application. In my application I'm going to run one iteration of unicorns, then I'm going to run two post-processing, and also I'm going to run a second iteration. Okay, so what would be my Tosca file? It would be first the FT2 node. We're telling it that we are running all of it in the HPC, in the Finisterra HPC, and then I'm going to define the first iteration job as type HPC nodes Phoenix iteration. I'm going to say that the iteration number is 0, and well, I put here as an example a deployment properties. In this case, as this is an example, I don't need to deploy anything because I already deployed manually in the system. But let's say I need, well, in this case, I need to build the software, to download it from GitHub. And create some folders and things like that. In this case, I could put all of this in a deploy.sh script and tell the orchestrator that the deployment is going to use this file with these inputs. Okay. Then I have the first velocity post and first pressure ports, would be these two jobs. I'm telling in this Tosca file that those depends on the first iteration, and also I have the second iteration which also depends on the first iteration, and for example the second velocity post-processing which is depending on the second iteration. If we send this blueprint to the orchestrator is going to run first iteration 1, then it's going to run in parallel those three jobs, and when this job is finished, it's going to run these two jobs. Okay, let's say for example we need to run 1000 simulation. We don't have to do all of these 1000 times. In this case, we will be able, not right now, but we will be able to put Finisterra 2 as a first box, and then another box which is going to be, for example, these 3 points, and it's going to be, okay, these 3 jobs, you're going to be running it 1000 times, okay? Things like that, all of this can be done in the Tosca file. let's see if the other job finish. Okay. Just simply, I want to show you. First, it ran the first job here. Then, when he finished, ran the third and second job, and both of them finish at the same time because they are dummy jobs and they are not doing nothing. And finally, it ran the fourth job. If well, I'm going to run just for you to show you the Phoenix. No, not here. I'm going to run you the Phoenix example, but we won't have time to see it because it ran for several hours. But just okay, uploading the blueprint, deployment created. Now I'm installing the deployment, so all the different deployment scripts that I would put in the Tosca file is going to be run in this stage. It's creating the node, connecting to the HPC. If we, for example, we want to copy input data, it would be that moment. If we for example, need to build software or for example, create different virtual machines, it could be that moment. And finally, starting the, as you can see, the first iteration it's going to be, it's been running right now, and we can see the first iteration in the HPC. Okay, you can see here the first iteration is going to be run for 3 hours or so, and then it's going to run the 2 post-processing and the second iteration. Okay, to finish, okay, that's well, I'd like to tell you finally different functionalities that I haven't shown you right now, but we are developing this moment. For example, containers or standalone execution. I've only run standalone executions, but in the same way, the orchestrator is going to be able to run with containers, in this case, Singularity probably. Victor will talk about that later. Also simulation interaction. I haven't interacted with the simulations right now in these demos, but it's going to be possible. Also, as I said before, iterative execution. So if you have different loops or things like that in your application, it can be done in the orchestrator. For example, one functionality that I think is nice is to be able to run different simulations at the same time with different parameters in order to see which goes better. Also freedom to choose HPC infrastructure or not. In this case, I've run all of this in the Finisterra 2. In the future, for example, you could have a node that would be generic HPC, and the orchestrator will decide where to execute what. And also, I've only run jobs in the HPC, but in the future we will be able to use virtual machines from cloud providers. Okay, that's all from me. I don't know if you have questions. I think maybe it's a lot of information. So, okay.
I've got about 6 questions. Do we have time for that?
Okay, let's.
Just let us discuss separately. Do you want me to discuss it with you separately?
Well, start with the question and we'll see.
Okay, so just a quick questions. Do you have any kind of framework of AA? So are you using some kinds of single sign-on or integration with other kinds of authentication providers?
We haven't started with authentication and authorization. But in this sense, this is something that we have to discuss. In principle, it's not an issue or things like that. I mean, we have a lot of options, and we'll choose the one that will fit best for us.
Okay, thank you. My other question is, do you have a model for actual charging for licensed products, or is it planned to use it as an actual marketplace?
Yes, well, the Orchestrator with the monitoring, or mostly the monitoring, is going to do the accounting part. In this way, we don't know if finally we're going to be charging for it or how we're going to be charging. So that's an open question that we will be deciding it at the final of the project, seeing the needs or I don't know, the license of the different applications.
Okay, so there will be some kind of feedback from the resource, how many of the resources are actually used, and some kind of accounting background will be actually connected to the resource itself, if it's got used all of their allocated resources. Okay, that's under planning.
Yes,
okay.
sure.
My question is, what kinds of hardware are the nodes themselves? So you've specified the nodes, and then you've just submitted batch scripts to the HPCs. So the nodes themselves are currently HPCs or some kind of parts of them?
Well, this is something that the architecture or the design allows to have only parts or whole HPC. In this case, the first test, we are using the Finisterrae 2 at whole, the complete Finisterrae 2. I'm also started to test it on the SCE infrastructure, which is actually an HPC simulation, because it doesn't. They are real PCs. So the orchestrator, what it's going to do is to have the information of the monitoring part, plus statical information, okay, or static information. Plus also, for example, you in the Tosca file, you will be able to, let's say, for example, you have some job, but you can say in the job, I only want that this job run in HPCs with nodes with more than 24 cores, for example, things like that. So the orchestrator is going to, for example, in this case, not use SCE infrastructure for this job. This kind of thing will be possible, and at the end, the orchestrator is going to be agnostic of the infrastructure, and is going to decide the modeler of the application or the mathematical frameworks, going to let him decide the restrictions of the infrastructure that they need.
Okay, thank you. Last question is about the remote visualization. Do you have any kinds of planned software to use? Will it be HTML5 based?
Sorry, 5?
HTML based, so it will be browser based.
Yes,
okay.
Yes. We're planning to use Prometheus as a core. As the main point of all the metrics, okay? But Prometheus is going to be reading, for example, in the case of CESGA, is going to be reading from their own monitoring system, and also is going to be reading from the different infrastructure or the different other monitoring system, okay? Prometheus is going to work as a hub for all these metrics. From Prometheus, we plan to use Grafana as a user interface for these metrics, because Grafana has different features, as I said, for example, to have different dashboards for each user or for each application, so we can show exactly the metrics we want in that time.
My question is.
Visualization of the results.
Yes.
We plan to use Paraview Web.
Okay.
Yeah.
Okay. Thank you very much.
Okay, thank you.
Any other question? Somebody else?
I have to find. Yeah, when Johan presented the pilots, there are some pilots which clearly require data, at least on the 3D air quality, I think. How about being able to handle something like data simulation, or the fact that data can arrive in the simulation to eventually correct the trajectory of the simulation?
Mm-hmm.
Do you think that's something that would be designed from
Yeah,
from
sure.
directly in MSO4SC, or is it a next step? Like
Yeah,
after?
it's going to be modeled again in the TOSCA. For example, let's say this example. Let's say, for example, we have here job 1, which is going to generate some data, and this data has to be able for job 3 or job 2, for example, or maybe job 4. Let's say this could be a calculation job, but this could be a data movement, for example, job run in a virtual machine, for example. Things like that. I mean, from the side
So it
of
could be data acquisition.
Yeah, for example.
Like you get data from the outside.
Sure. From the orchestration and monitoring part, it's going to be as open as possible, and all the things that you need to do in the application, let's say dynamic data movements inside the simulation or things like that, it's going to be modeled inside the blueprint, so the orchestrator, when it sees all the jobs that it has to run in each part, is going to run them.
And so the data then,
Sure, because
that is acquired, is stored in CCAN.
No, CCAN is going to be like well, it's a catalog, but it's designed as an heterogeneous storage system. So in CCAN you will have some data sets with different data files, but actually this data, it's not inside CCAN or storage in CCAN, it's stored in a third-party provider. What the orchestrator is going to do is to ask CCAN where actually this data is, and then it's going to if necessary, of course.
Okay, so what I meant by CCAN is that CCAN holds all the information about data. Maybe it doesn't hold the
Yes.
true data, but it knows where all the data associated to the simulation is.
There could be particular cases in which, for example, you don't want this data will be in the CCAN, but in your deployment scripts or embed in your own executions, you can put there some data movements if you want. Okay. So the main idea is everything. In theory, would be possible. Now we have to decide which things are what we want to do. Okay.
I have some more. Yeah, let's.
Okay, we are a bit delayed. I would say we're a bit more than 20 minutes. So if you have more questions, now we may have a fast coffee break, very fast one, maybe only 5 minutes, then come back to have the other presentations, and then we're expected to have a longer coffee break where you can talk with the presenters if you have more doubts or whatever. Okay? Okay. So let's have now these 5 minutes, okay? And then we come back.
Okay. Thank you.
So CCAN is all the info.
Oh, yeah.
CCAN. drifting on by, you know how I feel. It's a new dawn, it's a new day, it's a new life for me, yeah. It's a new dawn, it's a new life for me. Drifting on by, you know how I feel. It's a new dawn, it's a new day, it's a new life for me, yeah. It's a
Before that, I have to make also another announcement regarding the order of the presentations, because we were going to have two presentations, but and then the coffee break, and then the presentation from Prace. But unfortunately, Oriol has to leave a bit tight on. We are a bit delayed with the presentations, so we will move the coffee break after the talk from Oriol Pineda about Prace. And also, in this way, we have time to talk with him in the coffee break about questions and so on. So sorry for that last-minute change in the presentations. And now we start with Ákos Kovács and Tamás Budai, and they are going to do an introduction and comparison of different Linux container technologies. Thank you.
Thank you very much. Nice to meet you here in person. I'm Ákos Kovács from Széchenyi István University, and let me introduce my colleague Tamás Budai, who will hold the second part of this presentation. Our presentation title is Comparison of Different Linux Containers, and in a short agenda we have some discussion of containerization techniques. After that, we present the most commonly used container techniques or containers. After we present some benchmarks, first part some synthetic benchmarks, because they are good, because we know what we are waiting for from synthetic benchmarks, and then Tamás will be present some real-life application benchmarks as well, and we will show you our results and some discussion and conclusion at the end. First, some discussion of containerization techniques about Linux containers. They called lightweight virtualization as well. I will show you why. It's using mostly the host Unix kernel, host Linux kernels. From the host, it seems as a separate Linux processes only, not a whole virtual machine or whole something like that. And for the biggest advantage, we can use some different distributions, Linux distributions, as well with container technologies. We can see the main difference between virtual machines and containerizations. With virtual machines, we can use different versions of Linux kernel. So if you want to use some application which requires some special Linux kernel modules or something like that, then the virtualization is your solution. But when we use containers, we use the Linux host kernel, and we only have libraries and applications separately. We can see that these are the virtual machines and these are the containers. The VM are bigger, of course. So, the most common Linux containers. The first container is LXC, which is Linux container. It was the most, worst widely used Linux containers. It is using C groups to limit different things like how much processor unit does we use, or how much memory does we want to use, or limit the I/O and something. The Docker is an extension of LXC containers. It extends special kernel modules to improve the separation of the different containers. But the biggest disadvantage is it uses a server client architecture, so we have to use Docker daemon, which requires root privileges to use Docker in a HPC or on a normal PC. The different Linux containers too is about singularity. Singularity is intended to use in high PC environments. It doesn't require root privileges, which is a big advantage. It uses the same user inside and outside in the containers. It is compatible with Docker. As we can see, we can import Docker images, which is widely used, to Singularity and use them as native. And we can use InfiniBand and GPU accelerators as well, mostly out of the box. This is the good. Okay, the test system. We use the Huawei Blade servers to test these containerization techniques with Ubuntu hosts, and for that we used two computers, each with the same configuration, and we used 10G Ethernet for benchmarking network performance. Synthetic benchmarks. For synthetic benchmarks, CPU tests were made by CESGA. It is an industry standard benchmarking tool for CPUs, and network tests with industry standard Hyper-2. These are the versions we used. Benchmark 1, the CPU test. The CPU test, we calculate with CESGA the first 100,000 prime numbers, and the lower is better. So as you can see, the total execution time, we have to manipulate the interval of viewing to show the difference between the containers, the virtualization, and the native running as well. So it is less than 1% difference between virtualization, containerization, and native running as well. For the network test, there are a little bit difference. We used IPEF tool to see the measurement throughput of the Docker, LXC, Singularity, KVM, virtualization, and native as well. As we can see, Docker and LXC has a little bit decreased performance. To show that, we measured the TCP retransmission rate, which is a network performance limiter, because if we have a lot of retransmission, the one host retransmit a lot of data. For example, Docker and LXC has more than 1020 or 1500 retransmission rate. As you can see, Singularity and native are almost or as well as 0. To see what's happening, we have to understand the networking of the containerization. If we have a bridge networking, which is default configuration for LXC and Docker, we are using a software implementation called Linux Bridge to ensure the container networking reachability. But after we use a host networking configuration, which means that the container injects her own packages to the host networking, then we have the corrected results. As we can see, now we have all the same measurements. We have all the same transmission or throughput in megabytes. As we can see, the retransmission rates are almost 0 or identical to 0 as well. So these are the synthetic benchmarks. And I asked Tamás to show the real-life applications.
Okay, thank you. Well, as Ákos said, we have made some synthetic benchmarks, but is this thing on? Okay, then you can hear me. So the synthetic benchmarks showed us where we should start with these containerization techniques, but if you want to have a good impression on how you can actually use it in this project, then it is important to test with real-life data. For this purpose, I have made several tests using Fil++ and the included Fluid toolbox. As I was running the lead-driven cavity problem that is also inside this toolbox. I only changed the number of iterations to be reasonable, and so I didn't have to wait weeks to finish of the simulation. Well, to have a good picture, I have tested by running with 1, 4, and 16 MPI processes. So to see how well these containerization techniques can scale with MPI applications. And for the reason Ákos mentioned that bridge networking cannot be used for this purpose because of the big overhead, I used host networking in all setups. So the networking is host in all of these tests. And to have good results, I have made all of the measurements 5 times and then get an average from them. So the most simple setup was the native and single host, meaning you have a host operating system and the Fil++ application running on it natively. Well, it's not a big deal. You can also use Fil++ like this. You can pull it from Docker Hub and use on your own computer. It's not so important, but for a starting point and to have a good point to compare the other solutions, it must be done. So that was the first measurement. Then I measured the same runtime with the same configuration within Docker, and then with the same thing in Singularity, and then compared the results. Well, as you can see, you cannot see the difference, meaning that both Docker and Singularity performed very well when run on a single host. Well, it's not a big deal. We already seen that in some benchmarks earlier, but that was something that must be done to evaluate all these solutions. So it's all fun and games if you have only one host OS and only one container running on that. It's no big deal. Most of the problems arise when you have to use MPI or some interconnect to communicate and run your simulation on multiple nodes. For that purpose, that's why we use 2 nodes to have some tests with MPI. As you can see, I also did the native test like in the first place, but with 2 hosts. I also did the same with Docker, only Docker, firstly, the Fil++ application running natively on one side and running inside Docker on the other host, and then running Docker on both of the hosts, and then running Singularity on both of the hosts. Well, you may ask, there's something missing here, the native Singularity part. I didn't make that test because when I tested with the native Docker setup and the Docker setup, they showed very, very little differences. So I don't think that it's necessary to measure the Singularity and the native one. It will yield the same results. Well, as you can see on these pictures, it seems like a very easy thing to set up and to do, but the fun begins when this dashed line, the MPI, crosses the borders of the containers. There are some problems that can arise there, but if you overcome those, then you can actually achieve very good results with Docker and Singularity. As you can see, similar results, similar things resulted from these measurements. Both Docker and Singularity performed very well with host networking and MPI. It is important to mention that this time I used MPI over TCP, over IP. Most of the time in HPC infrastructures we are using MPI with InfiniBand or such interconnects, and there is the problem with Docker. Docker cannot play very well with InfiniBand, but Singularity can. Well, for a little bit of conclusion, we had very similar results by using synthetic tests and using the MADF Fil++. And we have seen that both Docker and Singularity has minimal performance impact in terms of CPU. So both could be good candidates for the infrastructure. But if you take a step back and see the bigger picture, Singularity can solve many problems we had with Docker and UDocker. I think that Javier and Carlos also can elaborate on that. But with Docker, we have so many problems like different user IDs and such. Singularity solves most of these problems and can be used as a solution for HPCs. So, and also it has simpler image management. We didn't discuss much about the image management today, but I think it is important to note that Singularity operates very, very easy or very simple images. These are basically files, file systems contained in a single file. The big or the good thing about that is that it allows us to create our own image management. We don't have to use Docker Hub or the implement or the included solution that the containerization technique has. We can do our own image management with Singularity. We can decide, for example, if we want to download it via HTTP or via FTP, or we have all the possibilities. So, okay, I think that was all from our part. I wanted to shorten it a bit because we are a bit late. Do you have any questions? Well, if you have, we could discuss it later. Okay, thank you very much for your attention.
Fast. And now we'll be having the presentations from my colleague Victor Sande from CESGA, and he will be talking. Well, he will be actually doing two presentations. One about the fast deployment of complex applications in the infrastructure, and the next one will be a demonstration of pre and post processing with remote visualization in the infrastructure. Thank you, Victor. You can start.
Hear me? It's good. It's okay. Okay. In this lecture, we are going to give an basic overview about the deployment, the main deployment issue, what is the portability, and the portability is a problem that is strongly related with other life cycle stages of one of these big software projects. And we present Docker, that is Docker or another technology, containerization technology, as the solution in order to get a fast deployment in our infrastructure, for example, Finisterre 2, but also in other infrastructures. As a starting point, I want to remark that currently in this project are involved several software with different requirements, and also several infrastructures like Finisterre, Plexi, and Sequana, all of them with different configurations, different hardware, different operating systems, and applications environment. If we focus in the software, particularly in the compilation stage, in this kind of projects involved in this project, we found some several. Well, we can say that all of these projects, software projects, are really complex from the point of view of the software architecture, but also if we talk about the relationship of this software project with its dependencies, libraries, compilers, and configuration like environment variables and these kind of things. In order to perform the compilation of this kind of tools, they usually use build managers like AutoTools or CMake in order to perform and manage the whole building process that usually involves these steps like download, configure, build, test, and install the project itself in the infrastructure. That can be a personal computer or, in this case, an HPC cluster. These tools help to to search dependencies and to resolve requirements in order to ease the compilation process while we try to do it in a new infrastructure through the feature of cross-platform compilation. Another stage involved in the life cycle of this application is the integration. It means that when you try to move the software into a new machine and reproduce the build process, is strongly related with the previous slide about compilation, and it tries to perform this compilation in a new machine, ensuring that all is working properly. With the integration, in the integration step, we add the infrastructure variable, and in other when we use continuous integration, we try to use several infrastructures, one or several infrastructures, and reproduce the integration step several times, usually per release or per commit or per tag, in several controlled environments. And what means controlled? But we cannot include all the possible infrastructures in a continuous integration process. We usually have several operating systems or several libraries versions of these kind of things. What is the main purpose of continuous integration? The early detection and fixing of the issues found while performing the integration stage, in order to avoid the integration hell. The integration hell refers to the process of building all the environment in order to have your application, your software project, running in a new machine. Usually, building the dependency matrix is a nightmare, and related with several libraries or tools, and each one of these libraries and tools has its own life cycle and several versions, and not all of them works together, and it's really hard. In our experience, some installations that are supposed to be straightforward or easy, at the end takes weeks or months in order to have the application working properly in our infrastructure. Okay, when we talk about deployment, in the slide, in the previous slide, we talk about this new variable that it is the infrastructure, and in the deployment stage, we fix this infrastructure in a production infrastructure, and when we deploy these tools, we try to reproduce again the integration process in these infrastructures, focusing in getting good performance results and have the software system ready to be used by the final user. Usually this process requires to satisfy the dependency matrix that from the point of view of HPC cluster means to install a complete hierarchy of libraries that must live together with other versions of libraries in the compute nodes. Usually needs to do custom fixing of the compilation process. Sometimes we also need to adapt the software, and depending on the version of the compilers and these kind of things. And at the end, underlying these slides, the same problem is always present, and the problem is portability. And when we mix several infrastructures with different kernels, different hardware configurations, different operating systems, different version of libraries, and all these variables must work together in order to have your application running on the infrastructure. It is a big problem. These are the main points. But we experience these problems in the deployment stage, but from the other stage of the life cycle of the software, there is a big work in order to avoid the problem, but finally we will find it in the deployment. A good solution, the solution we find and we adopt for this project are the containers, well explained by Ákos and Tamás. I cannot add anything more about talking about containers, only to remark that from the point of view of the final user, you feel, while using containers, you feel that you are in a different operating system, container system, and you have available all the requirements you need contained in this operating system, and isolated from the rest of the applications installed in the host. Okay, I am going to avoid this slide. Okay, finally, which benefits we found from using containerization and related with portability. Well, not only related with portability. Like Tamás and Ákos said, is a lightweight virtualization tool, because you don't need to load a new kernel, you don't need to reserve the amount of space is going to be used by the container, because the resources are directly shared with the host. The environment from inside within the container is secure and isolated. Like they say, the performance penalty does not exist. And another good points are the usage of containers empower users and developers. Users from the point of view of while you are inside a HPC cluster, you usually are a normal user. You cannot be super user. You cannot install anything using tools like YAM or apt-get or this kind of tools. And while using containers, you are able to deal with the system like as you were super user. And for the developers, they can decide how to deliver their software. They can decide which libraries go inside, which environment variables are defined and interact with your software, and give it directly to the users or HPC infrastructure ready to be used with minimal tuning from the HPC cluster. And this is why, at the end, the deployment of a container is as easy as to get the container, do a small step of bootstrapping the image in order to maybe install some dependencies required for the infrastructure, like library, InfiniBand libraries or these kind of things. And it's something that can be automatically performed, and the container is going to be ready to use. Okay, it was the first part of the lecture, and in the second one we are going to show a small demo. I have recorded some videos in order to do it more agile. Okay. What happened? Okay. Okay. The next lecture is we are going to show a small demo focusing in the execution of these container technologies in some steps involved in the workflow of this application, pre and post processing. And also a small video of the creation of a Singularity container. Okay. As Tamás and Ákos said, technologies that were tested were Docker, Singularity, and from CESGA we also check uDocker that we finally installed in the cluster. The features of these technologies are really similar between them, without going too much deep. But the main features for uDocker and Singularity are the portability, something that I already told, and that the images used from uDocker and also from Singularity can be downloaded from Docker directly without any effort. Okay. Now we are going to show how to create a Singularity image. In this video, I use my personal computer. I am working in my home, and I have. We can see that I have only two scripts. One performing the steps we need to create the container, and the other is a bootstrap definition file in order to install the operating system and also a test application inside the container. Okay, if we take a look, if we take a look at the content of the demo script, we can see that we only have 3 steps. First step, create the Singularity image and reserve some disk space, in this case only 512 megabytes, inside the file called mpi hello world.imh. In the second step, we are going to install an Ubuntu operating system installed in the image using the bootstrap command of Singularity and the bootstrap definition file that I told you that it's called mpi hello world.def. And then in the last step, we are going to run Singularity with mpi run in 4 tasks and execute a typical hello world application and see the result. If we take a look to the bootstrap definition file, we can see that it can be very simple, but of course it will be complex if you try to install another complex applications. But we want to reproduce a simple compilation of one C file. It starts with the header section when we say to Singularity that we are going to use Docker Hub to download the latest Ubuntu distribution. Then we have 2 sections, the post section where we install some software within the container, and in this case the OpenMPI libraries and the wget utility tool in order to obtain the file we are going to compile and execute later. Okay. Then we clean the installation, and in the last section, the run script section, we tell Singularity that the image we are going to create will execute as default the Hello World application. Okay, if we run the demo script, sorry, I speed up a little bit the process to be more agile. We can see the steps I described previously. The user will feel that he's using the apt-get application to install software inside the container, and it will resolve all the dependencies of these libraries by itself as apt-get do. Okay. And at the end, I'm going to stop it now. We can see that the typical hello world message, all the tasks involved are telling, are presenting itself and saying I am 1, 2, 3, or 4 task. Okay. If we go back to the presentation, now I'm going to show you 3 videos more, trying to represent the simplest workflow to execute one of these mathematical frameworks, starting with the pre-process, then executing a simulation using Field++, and then showing a post-process with ParaView. The most important thing from my point of view of this demo is to show you that there are several container technologies involved and also native installations, and these tools perfectly fits between them and are compatible. All of them, when containers execute the applications inside of them, but are able to interact with the user home directory in order to obtain the input and write the output. Another important thing of this workflow is that the process is going to run sequentially. Simulation. For the simulation, we are going to use 4 tasks into different nodes, running Singularity in parallel, and finally, for the process, we are going to see the results of the Field++ simulation sequentially with ParaView. In order to, another important thing is that we are going to show you this workflow, or this simulated workflow, using a remote visualization tool called BNC that is already installed and working from CESGA, and it's expected to be included in the portal. And also, this workflow will be managed by the Orchestrator, but we are going to see it from the point of view of the cluster. Okay. Okay, can you see it? Okay, I'm going to restart the video. You can see that we are showing a web browser, and from this web browser we can see a desktop, and the user will experience like he or she was using its own computer, but inside a web page. Okay, now we are entering the directory where I have the demo, and we can see that we have 2 different scripts. One is a Python script that is going to be read and executed by Salome, and the other an input CAD file, geometry, that is going to be meshed. To load the Salome platform Docker, we need to load the uDocker module and then the Salome module with the lmod module system. And after loading these 2 modules, we have access at 2 different scripts, Salome terminal application and Salome graphical user application. To run Salome terminal, in order to run, we only need to call it and add as an argument the Python script that is going to read the CAD file and compute the meshing. We are seeing how the container is loaded, and Salome is running inside the container, and finally it computes the mesh and writes the output file and UNV mesh in my home directory. Okay. The other way to launch Salome is with the graphical user interface. I'm going to show you. We are loading the same container, and the container is going to show us the graphical user interface. We can load the geometry module, load the CAD file used to compute the mesh previously, that is in my home directory, and we can see this CAD file, and we can interact with the CAD as if we were in our desktop computer. Okay, the same happens with the mesh we have created. We can load the mesh module and load this mesh. Okay, we can see the meshing. We can also interact with it, and we can create groups in order to reference boundary condition of these kind of things. Okay. We perform the first step, the pre-process, and we are going to launch Fill++, the singularity container of Fill++. Okay, again, I'm in CESGA, in my home directory of CESGA Supercomputer, and we are going to reserve resources in order to launch this container in parallel. We are going to use four tasks in 2 different nodes, and we only reserve 10 minutes for doing this task. Okay, we already have the requested resources, and we are going to execute this container. Again, we have scripts to launch this, to automate the launching of this application. First of all, the input files that we are going to use in this demo, and then a script. This script automates the the loading of the required modules. In this case, we need to load an OpenMPI version in order to use MPI run command, and then Singularity and Fill Toolboxes Singularity container. Okay, and these are the arguments used to launch the execution. We use the Fill++ toolbox fluid 2D, and this input file that is the same that I have in my home directory, and the run command is a call to MPI run to the container with 4 tasks and with the arguments, with the environment variables to export and the call to the executable. Okay, if we run this script, we are going to see the output of Fill++. First of all, it loads the modules. Here we can see that these 4 tasks are in 2 different nodes, and then the execution start and also end. Okay, now we are going to explore the results of this simulation. Okay, in the last step, post-process, with ParaView, that is natively installed in the Finisterre 2 cluster. We are going to use also the remote server, remote visualization. And, okay. Again, we have a script to do the process, to automate the process of launching ParaView. It only loads the ParaView module and run it in the remote desktop. Okay. Okay. We can see the ParaView as if we were in our PC, and we are going to explore the Field++ results. Okay, singularity. I don't know if the video is more agile than doing it live, but okay. We have here we have the results. We load the file, and we are able to see the simulation results and to interact with the mesh and post-process these results using this remote visualization tool without the need of downloading the results from the supercomputer to our own PC or something like that. Okay, we can see several fields, and also we can see the distribution of the elements through the different tasks. Okay, in order to end the presentation, I want to remark that we used the remote visualization tool VNC to do it, and it will be integrated with the portal, and also the orchestrator will be able to reproduce and to manage this workflow without the need of executing each script manually, like I did. It's all, I think. If you have any question, please ask me. And if not, we can continue with the next presentation. Please ask.
Have you tried on large scale? Did you try on a big problem? Because this is rather this is a small example, but how does it scale if you work with big geometries, big meshes, and things like that? Have you tried to?
I've not tried yet.
You haven't tried.
I only did the dummy test in order to be sure that the workflow can be executed. But there are some tests pending in order to create realistic geometries to create meshes and use them in real simulations and view the results with ParaView. Of course, ParaView is a well-tested application, and the use of it from Finisterrae to cluster is very common, and we have tested it in real environments and loading big quantity of data, but not with the other steps. Of course, you know how to launch Field++ with real test cases, and you are going to do it with I2 Brain and Hyphen Magnet, but I didn't do it yet. Another question.
Thank you, Victor. So now, in theory, we should have the coffee break, but instead of that, we are changing the order of the presentations. And now, Oriol Pineda from BSC, Barcelona Supercomputing Center, will be presenting the Prace services, so we can all benefit from this large European HPC infrastructure. Thank you.
Okay, so let me first thank Zoltán and Javier for this kind invitation. I'm Oriol Pineda from the Board of Directors of Prace, and I will introduce you our services and mechanism of access. So I understand there are some Prace users already here, some others that don't know anything at all, so I'll start from the beginning and give you some words about us. So Prace is the Partnership for Advanced Computing in Europe. We are an international association with seat in Brussels. We have now 24 members, of which 5 we call hosting members because they provide the large Tier 0 systems. Prace is governed by this Prace Council and managed by the Board of Directors, and is funded by the members, with some contribution by the European Commission through a series of implementation projects. So this is the HPC ecosystem as we see it in Prace. We see a first layer of Tier 0 systems Europe-wide. These are investments that no country would do on their own. Then we see the second layer of Tier 1 national systems, the systems that you all have in your countries. And then a third layer that we call Tier 2 of regional systems. It is university clusters and so on. And in Prace, we deal with the first layer and part of the second. So our objective is really providing Tier 0 capacity, capability, and diversity, and coordinating part of this Tier 1. Our scope is to fund open research projects for academy and industry, which are free of charge at the point of usage. And our services are this Tier 0 project access, then preparatory access with the option of giving support from Prace experts. We have also programs to support SMEs, and then Tier 1 for Tier 0 preparation, Tier 1 project access, and last but not least, we have a wide offer of training. Just to show you the systems that we offer now in this first layer. These are the most powerful public systems in Europe, and you will recognize a few of them. So some numbers to give you an idea. Prace started in 2010. Since then, we have enabled 524 scientific projects, awarding more than 14,000 million core hours. We put 1,000 million to make the difference between the European billion and the American billion, so at least it's clear we are not offering too much. We have also offered this to industries, supporting more than 50 countries. In terms of training, we have trained more than 10,000 people by the 6 Prace Advanced Training Centers, and combined we have now a peak performance above 60 petaflops, which is comparable to that of the Chinese, the Japanese, and the American systems. Not bad. Okay, this slide is just to show you that we are really transnational. So there are 5 countries put in the systems, but the projects that go there are typically from 60 to 80% out of those countries. So we are funding all Europe, not only our stakeholders. All Europe and all the world, in fact. It's not limited to Europe yet. Regarding training, we have Prace training centers, Prace advanced training centers. The difference is, again, the scope, national or European-wide. Something that can be interesting of you is these on-demand training events. So you have a large curriculum of training, but whenever we identify something that's not in this curriculum, we can make a proposal, make a plan, and have this on-demand, even on-site training event. Then we have programs for undergraduate and postgraduate students, summer schools, and finally we have one massive open online course that you can register and follow from home. Like I said, it's quite important for us, the access to industry. So since 2012, we offer this. Again, the only condition is that they have to publish the results, so it has to be open research. And we have also these programs to attract and to foster SMEs into HPC. Some examples of projects that have run into Prace. For instance, Renault, the car company, they improved case safety through a large allocation of 42 million core hours. Then we have also worked with Sanofi in drug discovery simulations. And then one SME working with ship survivability and aquaplaning for cars. So quite really interesting projects. Just quick slide about a lot of companies that have benefited from Prace resources. Okay, now talking a bit about the present and the future. The objective of Prace is really securing access to HPC in Europe. So Europe needs to guarantee access to world-class HPC and maintain the highest standards in computational science and engineering. This really requires a Europe-wide competition. So we centralize all the review and ranking of proposals to get the best ideas and the best groups. Again, Prace has several systems, and in order to ensure the diversity needed by the user requirements, we have to coordinate all these policies. And finally, Prace also aims to coordinate the European and national governments into these funding schemes. You may have heard about something that we started, the Prace 2 program. So Prace 1 started in 2010. It was a program funded mainly by 4 countries, France, Germany, Italy, and Spain. And this created the solid basis for Prace. Now this program finished, we are in the Prace 2 program, where all the Prace partners contribute in one way or the other. And we are looking towards sustainability. This program started recently, will run into 2020, and will allow us to really continue beyond this enabling science and in HPC in Europe. So again, some more numbers. The systems in Prace have a capability comparable to a system of 5,000 nodes with 2 CPUs, latest generation, so typical large supercomputers, and of which each hosting member contributes 40%. So if we add it all, it's like we are offering one dedicated system of 10,000 nodes. In terms of cores, could be 500,000 cores, depending on the architecture. And we are giving some 4,000 million node hours per year. So quite a lot of resources. This Prace program has something which is new and quite important and can be also useful for you. It's these high-level support teams. So these are the levels of user support that we define in Prace. Number 1 would be help desk and really quick support. Number 3 is more code enabling and scaling of applications up to a few months. And then level 3, really code refactoring. We have this new program of the high-level support team that will work on level 2 and level 3. And there we can identify topics for collaboration. Then there is a level 4, which would be long-term projects, but this is something already funded by the European Commission and the Center of Excellence, that some of you have also links. Now, what we do, of course, we receive more proposals that we can handle. Our subscription is about from 3:1 to 4:1, so we can only accept 25 to 35% of the projects we receive. And to make the selection, we do a transparent, independent peer review process with different actors involved in order to really get, in an independent way, the best proposals. So it starts with the calls, then an administrative evaluation just to check that everything has been filled correctly. Then we rely on external expert scientific reviewers. Maybe some of you have been contacted. If you are interested, we have a database, so you can sign in. Then all this input is taken by an external committee, the Access Committee, that does a ranking of all the proposals based only on scientific excellence. And then a different committee distributes the resources. In this way, we have a transparent process, a fair process to make this distribution. Finally, I am sure you all agree that simulation is now the third wheel of science with theory and experiment. We are all here to make it happen. We on one place, you maybe are on a different one, but we can work together to really make this simulation work in the future. So I plan my presentation slow in case there were questions to allow for time. Thanks for your attention. Maybe this was too quick. Okay.
1 minute, 1 second, please.
I can speak loud.
No, but it has to be recorded.
Yeah, so they get your sound.
Users, you know.
When you look at, it's really like kind of maybe a weird question. Huh? I don't know. It's to enlarge HPC access. So I teach at the university, and currently students don't have directly access to an HPC facility. Mm-hmm. And I was wondering if in time Europe could not provide like free access to HPC. Of course there would be that, but with a very limited amount of hours, mm-hmm. but that it's extremely easy to have access to it. Like for, you know, you want to have a service on the internet, you have always like a free access, and it's extremely easy to have access to it. I visited a few weeks ago with some colleagues from Strasbourg, ETHZ in Zurich, and actually all students have access to HPC facilities, not necessarily associated to courses, but to just because they are students there, mm-hmm. so they can experiment on it. And in general, I mean, so the question is, do you think that in a few years we could have access to large number of cores, maybe not a lot of hours, but easily access, and it's kind of facility which is right on the shelf here?
Okay, so I see this as two different options, meaning that some universities have clusters or small HPC systems that they can give access for free and easy. In the case, I guess you mean for large systems, and in the case of Prace, we have this, I just put this slide, what we call preparatory access. This is a quick access, meaning that from the moment of your request to getting the resources, it should be 1 or 2 weeks. This is for small jobs, like scalability tests, like small developments, and they don't need really, I mean, we try that they are related to large scale projects in Prace, but it's not mandatory. So it can be a point of entry for these small jobs tests, developments of code that you would need small allocations. By small, we would say 50,000 core hours or 100,000 core hours. These would be our mechanisms, which are already in place now. I don't know if this is...
I mean, I think at the universities we could have like easily access to HPC. Like you register as a student, you are a professor, you are a researcher, you have automatic access to the facility. But then eventually you want to climb up, you know, and go to higher level supercomputers to test with many more cores, because that's the point here. And so if you want to run on several tens of thousands of cores or 100,000s of cores, you have to go to tier 1 or tier 0.
Yeah.
So the point is ease of access to these facilities.
So it's all about the complexity, no, not the complexity, the size of your problem. So if it's, again, for tests, we have this preparatory access, which really the name is not the best one, but you could see as a small-scale projects, most for development, not for research, but to test scalability, to test and with development. And this would be this access, of course, only to these 7 Prace systems, but this would be in line to what you're saying. In fact, if you were in ETH, I guess the students have access to PISDAINT as the major HPC system there, and PISDAINT is one of the Prace systems now, and it follows the same rules like the others. So it's, I mean, the access is not through the universities, it's through Prace, but it doesn't make a difference, meaning that all students or researchers, well, maybe not students, researchers, we could say, have access. But really, Prace is looking for, further services or further communities to come in. So this would be something to explore if this is not enough.
Thank you. No? Any other question? Our questions, so then we can have a break for that.
Okay. No, another one.
We have the coffee break.
So we talked about container technology before, and I think that some supercomputing centers are experimenting with it. What is the roadmap? Is there a roadmap for this kind of system?
In Prace, you mean? Okay, so good question. Now I will introduce myself with a different name. So I am in Prace, but I also work in the Barcelona Supercomputing Center. And I know that at least BSc is working in containers. So about Prace, right now the systems are funded by 5 countries. So these 5 countries define the policy. Meaning that Prace is the only thing that wants is integration and coordination, but is not enforcing policies on any of this. I know that at least for BSc, containers are important because we have 1 or 2 groups working on them, and I'm sure it will be something to be considered and included in the future. But from Prace yet, we accept these 5 countries' policies. So it's mostly to convince the French center, the Spanish center is mostly convinced, but then Germany, Italy, and Switzerland. And you will be able to use them in the ones that you convince.
I think we have one question or comment.
Okay, Zoltán, easy one, please. You are from Prace.
Yes, and sorry about that. So actually, Prace project includes some activities related to actually enhancing services. And the current 5IP project has a dedicated task to actually evaluate containering techniques in WP6. So there's a work package on evaluating current services and enhancing. So this is now in the status of evaluation. Hopefully, in the near future, it will be deployed as something that's actually supported as a core service, maybe.
Okay, thank you. I mean, now you see that I know a lot about Prace, Board of Directors and Council, but I don't know what's really going on in the inside. But had some clue, but I was not sure, so thank you for clarifying.
More questions, maybe?
Okay, if you want this coffee break, we can talk more informally about other things. Okay, thank you.
So now we have the coffee break, and then we have the innovation game from them.
I propose to make the coffee break shorter than
Yeah.
maybe 15 minutes.
Until 6, maybe. Yeah. 6. Good.
4 to 6.
Let it fill your soul. Let it fill your soul. Your soul. Let it fill your soul. Your soul. Your soul. Let it fill your soul. Your soul. Your soul. Your soul. Your soul. Let it fill your soul.
as perhaps was originally thought. But what I wanted to use the time for now, and we can talk again tomorrow afternoon, is to understand a bit better how the project is going to change the way we do things in terms of getting working with customers or getting contracts or providing our services. Okay, so I've worked more in the HPC side of things over the last few years, so I understand a bit more about what's going on at that side. What I don't really have much knowledge of is the mathematical world and how the tools that are made at the moment and the tools that we're going to be putting onto the HPC structures, infrastructures, currently operate and how that is going to change with the project. Okay, so if we think at the moment, more or less the value chain for what's going on in the project, you've got the hardware, you've got the supercomputation centers which take the hardware and turn it into supercomputational capacity. This is then provided sometimes as a service, sometimes more through more traditional ways. You then have the mathematical tools that are going to sit on top of that infrastructure, which are going to become HPC enabled or cloud enabled and available as a service in principle. And then these are used then in simulations, which finally give some result for some end user who says, I need a simulation on what happens in these wind farms or in these gas turbines or whatever. Okay, so what I thought we could do is go around the room a bit and people could say where they sit currently in that scenario, in that value chain, and say what they're doing now currently in terms of where is their major business coming from related to this field, and how do they go about doing that business, or whatever channels they use, and how is that going to change with a project. So once you have the MSO portal that can provide the computation, that the applications can be developed on top of the infrastructure and then provided to third parties. And once those applications can be collected and used in simulations, how does that change things for you, for your organization? Okay, so without further ado, I think if we start just doing a round table is the easiest way of doing it rather than looking for volunteers. So if you just say, I'm currently in this area, this is what I do now, and this is how I expect the project to change me, we can start to build up a picture of some extent of where we can take the project, okay, and what are going to be the main critical success factors, if you like, of getting there. Okay. So, you've got the microphone.
Do you want me to?
Do you want to start, or do you want to pass the buck?
I think I should pass by.
Thank you. So I'm in atmospheric sciences,
okay,
in air quality modeling. Lots of computations to do. I seek the chance to migrate our computations to cloud services from local servers.
Okay. So currently you are writing applications to run on the hardware yourself?
No,
no.
I haven't got to writing an application yet. I'm
okay,
just looking for the possibilities.
Okay, so you're taking the software that's been developed by other people and you're using it to create simulations?
Exactly.
Right, okay. And, sorry, I keep going. What are the key, in terms of performance, because we've talked about the cloud to the HPC spectrum, how do you see, do you need simulations at both ends of a spectrum, or do you sit in one area of that spectrum, do you think, in terms of performance that you need?
In atmospheric science, we have a very wide spectrum, because for research you can live with a few hours a month of high computation time, but for operational weather forecast you need every day high capacities. It's a very wide spectrum, and it depends on the research topics or your task.
Okay. Okay, thank you.
So I manage a team of development for Field++, one of the mathematical framework, but also I teach, I work with companies, with other people in other disciplines, so develop new models, develop new kind of applications, or sometimes applications that we reproduce also applications that are available elsewhere. And what I would expect for the project is to shorten tremendously the time from, let's say, development to deployment of the applications. I think we managed to do that already with the mathematical framework in order to go from, let's say, a laptop design of the algorithms to, let's say, large-scale computation. So we are relatively happy with that already. But now the idea is to really shorten from design, laptop, to deployment. We have several companies who are interested in that. And also people from application domain who would be happy to just deal with web-based interface to launch simulation. They are users, they change parameters, they just want to, physicists, they want to do a lot of computation. So,
okay,
and the other thing is about teaching, really to be able to do teaching using new ways with these kind of tools and give access to.
And the applications you develop, they're normally sold, they're bespoke applications for specific client, or are they something that's more general that you sell to multiple clients?
Depends.
Depends.
Depends. Can be. On Wednesday we present some toolboxes, so it's relatively generic, but then we have also specific applications which are tailored for a specific customer or stakeholder. And we are definitely, we would like to be able to provide that as a service.
Yeah, because it makes more sense. I mean, it makes sense when they're generic services to be available as a service, but if they're bespoke, obviously you lose, you don't get the benefits because you can't scale up, right? You can scale with performance, but you can't scale with sales because you're only selling it to one client.
Yes, that's one thing. But also it simplifies the way the client is going to use the software. I mean, for them, it's really a simple, with a simple operation, they can have access to the software. Which was not that easy before, because we had to deal with their specific environment. And they are very, very constrained. I mean, at the university we are constrained, but in no way like in companies.
So would you normally set it up to run on their...
crazy IT departments.
But you would normally set it up to run on their infrastructure at present?
Yeah.
Okay.
We managed to deploy some application in their environment using this kind of technology. With Docker, but with Singularities probably.
Okay.
Be probably the same.
Project.
Yeah, that'd be good. Yeah. Sorry, there's a bit of an echo. Okay, do you want to pass on?
This, no, I don't have that one. Do you have an adapter? No. I only have HP.
Okay, well, we'll continue. see if we can get that up and running.
So I'm both a developer and a user of Field++ library. I mainly develop the Hi-Fi magnet pilots. So what I would expect of this project is twofold. Is on one side to be able to develop new models for our magnets rather easily. And the second one is that my colleagues from the conception teams can easily access to those tools and can run the calculation they want to, because they are the one with the knowledge about designing and so on. And I think they will greatly benefit from the use of this kind of software or these new methods.
So it will reduce the complexity for them, right?
Yeah, somehow,
okay.
Yeah.
Okay.
But at the same time, to also work on new models for new kind of magnets to account for new phenomena. Because the point is, we want to make more and more reliable simulation, in the sense that we are almost able to predict what will be the quality of the magnetic field we will generate and so on, because this is important for our end users who may want to have a very specific magnetic profiles, and that's
okay. And in terms of accessing those customers, do you think that MSO will change it when you have a portal that you can make it available as a service, so that people can discover you and use it without needing to perhaps interact so much with you?
Well, yes, this is an interesting question, because there are, well, in my field, there are a few labs involved on the world scale. There is a network of the European labs which may be interested in that kind of solution if they are open. We can also envision that it also extends to superconductor designers, like people from the CERN and from other research institutes, or from the accelerator community, for instance. But this would need some more developments to account for superconductivity, for instance, what exists today.
Okay. You any luck? Okay, thank you.
Hi, I'm a PhD student. I'm a developer also at Field++. I'm currently working on the Eye2Brain project. For me, this project can be like interesting for the really relationship part with the ophthalmologist. Because actually I'm working more on the eye part, but still, and I had the chance to meet some of them. Actually, tomorrow there will be a presentation by remote by one of them, and I really saw the need of some really mathematics and these computational tools for them, because they have already tried a lot of things, and now they are looking for something else, new ways to understand what is the physics. And the first trial that they made was about statistics, but now they are more interested in models. And I see this project in order to be able to give them some tools, and that is kind of black box for them. I think that they're really not interested in what is behind, but in the really on the like.
So they just want the tools, and take the tools and use them. This is
kind of new stuff for me. I'm always in the university, and they really care about the results, not all the process. They really would like something real and not something that is test or benchmarks or.
Okay, so from your perspective, they would like just to be able to log onto a website and click some tools, set it up, put in their data, and execute, and not have to worry about what there is behind it. Or is it
for what I saw in this, because I had the chance to talk with some of them, ophthalmologists, and I think some of them are more interested in what is behind. Maybe especially what are the limitations of the models, maybe some of them, but most of the time is really what can I put in and what can I retrieve and what the model is saying to me. And really, but still they are a little bit more still afraid of what is, and you know, there is still a barrier between the two. There are some of them that are they are now opening to this new feature, but it's still I felt really still a barrier between, and maybe.
And is that a barrier because they don't want to get into the hardware and how to set it up and all of the
because they don't trust.
Because they don't trust it.
They don't. They because they don't know what is. I think this is my opinion. This I don't know. I think that they don't know what is inside, and they don't trust what because they are used to do other stuff. They are used to see and make experiments and try with the experience. And instead, this one is kind of a virtual thing, and the most of the part does really don't trust. But some of them are opening, and I hope that with this big project can be like, you know, breach in the barrier.
Okay, thank you. Okay.
So hi, I am a research engineer, so I'm also working with Field++, so with the whole team. And I will join with what say Christophe just before, that most of people may be afraid maybe to with the first approach to Field++ because you have a lot of things to install. And what I see when I try to deploy on several machines is that the time you take from the installation to begins with mathematics be quite long. And I expect from this project that you can shorten the time between the installation and the use of the concrete mathematics of Field++. So.
Okay, thank you.
Hi, I'm Victor. I'm a technician from CESGA. I'm in charge of the deployment. I come from this environment, but I did different tasks in the past, more related with development, and I would like to get a wider perspective of this kind of projects, focusing in deployment, user experience, and also I would like to learn about things more related with management and the whole view of a project that is new for me.
Okay. And do you think for CESGA, for example, if you could set this up, this would be a viable service for UK? You say we have these frameworks set up running on the HPC, and we have people using them. How feasible would it be for you as a supercomputing center to be able to offer this professionally?
I think that it will be nice because, in general, main issue while delivering software from sources is the final user. Most of the issues from the final user are related with installation and deployment, and I think that avoiding these issues will agilize the other aspect of the usage of these applications, and will speed up finding another kind of issues while using it, about maybe with performance, with precision, with convergence. I don't know. Yes.
Okay, thanks.
Hi.
Hi.
I'm Vedat Durmaz from Mathematical Institute in Berlin. We do like molecular modeling, computational molecular design, or drug design as well. What I mainly dealt with the last years is among setting up and generating polymer models and and let's say also binding affinity models for little compounds, chemical compounds. So we want to estimate binding affinities to proteins or something. So I usually set up these systems and did the molecular modeling part in order to answer certain questions coming from project partners mainly. And here now we are trying to establish, to implement the software for binding affinity estimation in a user-friendly way. Mm-hmm. That is making, so there are many scientists like toxicologists or something that come up with a new chemical compound and want to know its binding affinity because they see some similarities to some other drugs or chemicals and they know this might bind to this or that protein, and this is what, and they are not able to set up these molecular systems for simulations, yeah. And that's where we come into play. We want to set up this, implement this on the CESGA system, on some e-infrastructure, and making it as easy as possible. So they just upload their small molecule, choose their protein targets from a database, and then they get their binding affinity.
Okay, and so currently where do they do it? Where do they execute it?
Can you say it again?
Where do they currently execute the simulation?
They do not do that. They have project partners as we are. We would set up the system because it's a little complicated for them. If you don't have that, that I would say, if you do not know how to handle the software and you have to work on a terminal and stuff, yeah, then you need someone that is able to do that, yeah.
Okay. Okay.
Thanks.
Thanks.
Okay, can you hear me? I'm Atke Rasmussen. I'm from SINTEF. That's a research institute. So our business is selling projects. And I'm in the business of building and improving simulation software, not using it. So I only use it to see that it works, and to convince myself that what needs to be done to it. So I think for us, taking part in this project is part of taking the software to where the usage will be. So usage is going towards running large ensembles for uncertainty quantification, running larger models for more precise resolution of fronts of things. And so we need to be there in time to not become obsolete. And also for us, visibility will be important. I think we need to we want to build new software. We're building software, and simulation software is what we do. So in order to have that as a continuing business, there must always be something new for us to build, and people must think that we are capable of doing it. Mm-hmm. So visibility is very important.
Okay.
Also, much of our research, well, it's published in papers, but decreasing the distance between research that goes into papers and actual software run by industry is also part of the goal here. And the improvements in deployability, ease of deployability is going to help us there, because if the users can very easily run the software and then, oh, there's this extra module, you just click an extra button and then you can test the brand new research that we have done, then that's so much easier to test and try out. Mm-hmm. Then, yeah, as you commented, you don't need someone. Then you don't need someone who's a Linux hacker and knows his way or her way around the terminal to do it, which is currently the state.
So if you're currently developing these simulations, would you see a market for yourselves to start providing them commercially or releasing them for others to do so?
Well, we have committed to an open source development model, and it's been a fairly successful business model for us. We provide improvements to the software. We build the software and add features that are interesting to people who are able to pay for those features. But I see that the commercial business around it would be like consultants using the software to run cases for other companies again. That kind of usage is happening already, but it's increasing, and I think it will be more important.
Okay, so you would see yourself as using the tools that were set up on the MSO system and refining them, adapting them, and then providing them onto your...
Yeah, I think that, people providing core hours at HPC systems and providing simulation services, we could use the software we make, but I don't see myself running that kind of business, but maybe just enabling it.
Yeah, okay. Thank you.
So my name is Johan Hoffman. I'm at KTH in Stockholm. So I manage a group of software developers, and also we have a lot of different projects together with the partners that are not necessarily close to computing, like medical applications as well. And this kind of platform, I think, would ease that collaboration, as has been said before, and also connect to various partners' data. So in our case, that would be you generate a lot of imaging data, for example, which feeds as input to these simulations. You would like to have somewhere to get these streams to talk to each other. And on the research and software development side, I see this as a way to disseminate this in a more effective way, because when you develop this optimized software for high-performance computing platforms, it's complex to disseminate to non-experts. So this would be a way to do this in a much more efficient way.
So you would say it was critical that we have ways that the data from third-party models from the end users can be put into the system.
That would be the first point.
And would that be a data transfer into the system to be used, or it could be accessed remotely?
It could either be that these users would upload their data and use our software, which is already installed. But if there is a way to get this data stream connect to some other way to transfer, or just stream the data, that would be also a possibility, I guess.
Okay.
And teaching, so I'm at university. So in particular, which may be possibly a pilot in this project, is a MOOC course that is a selected course at KTH. So a set of a few dedicated MOOC courses where there typically the number of students can scale, possibly. So, and how do you provide this computation platform for such a course?
Yeah.
And this would be an opportunity to do that. We have done that for non-HPC type courses, but if we have the ambition to teach these kind of courses, we would need a platform for doing that.
Yeah, which is actually fits in with a lot of work the Commission's doing now in trying to get, they change the vocabulary, but data scientists or dual specialists, and basically students coming through that know about multiple areas. They know how to make it run on HPC, they know how to do the simulation, and they know the maths behind it. So I think that actually fits in with the strategic agenda of where the emphasis is going with this.
Yeah.
Okay, thank you.
That's my main point.
I am developing I am a PhD student. I am his PhD student now, and I am working at the 3D air quality prediction pilot. And so I recently joined the team that's working on this project. So far my main concerns have been about development of this pilot. But in doing so, in developing applications that are, more visibly connected to the real world, I think that I am helping raising awareness on the potentials of mathematics and computational sciences as tools to help us improve our everyday life, because then you do a test simulation, you do a video, you send the video to a friend or whatever, and you post it on Facebook or similar or YouTube, and then people see it and people start maybe asking questions and getting interested, and I don't know, I think this is my little contribution so far.
Okay, thank you.
I'm Zoltán I'm leading the Hungarian HPC infrastructure. I'm here by mistake, I'm not in the project actually. For me, it's crucial to optimize HPC usage because, that's our infrastructure. So my goal would be is to reduce the amount people consuming for their own project. And the best way is to not letting them accessing the HPC directly, because typically they don't know how to write optimized codes, and they need a lot of help. So if we are offering them some kind of portal, when we can optimize make these applications portable, these infrastructure providers can benefit a lot. And for me, portability is the key, because as an HPC provider, we can see the technologies advancing, and we have new, cheaper technologies like accelerators, coprocessors, and we have new kinds of hardwares within these special technologies coming up from year to year. So we have to offer some kind of knowledge to the users themselves to utilize these new technologies, because if we are buying those newer and most of the time cheaper technologies to achieve the same amount of computing power, we are failing on the side when it have to be utilized. So we want to follow the new digital trends, but scientists are not able to follow them typically. And if someone in the community is able to achieve some major results, like optimizing for a specific architecture, then it reaches less scientists in their work group, because I think, I strongly believe they tend not to share these kinds of results, and in many cases these kinds of results are not able to reach the people or the scientists in the same domain. That's at least my experience. So for me, it's the portability. So if we have written an application before, it's easy to rewrite to be more optimal using the latest technologies in terms of hardware and software side.
Okay, so a lot of what you're saying is decoupling, basically, again, what we've heard before, decoupling the specialisms from one side to the other. Okay, thank you.
So I'm Carlos Fernandez from CESGA. Well, we are HPC providers of resources and, well, some sets of knowledge also. What we expect is to be able to provide these resources to a wider scientific community, and also, of course, to companies, for example, because we are working with some small companies doing some research. Always the most difficult part is to be able to port the software to the HPC resources and to use that software optimally in the so this is a difficult part. If we are able to reduce this time, the porting of the application, not only the porting of a specific version, because usually as I mentioned, the software is always developing. New versions are available, so we waste a lot of. We are using a lot of human resources for this porting, and sometimes it's a kind of a frustrating process for our staff and also for the researchers that are doing that, instead of doing research and optimizing the algorithms and that part. So we want to be able to reduce this effort in some way, and to also to attract new user communities.
Okay. Okay, thank you. Anyone else want to add some more comments? So I think there's quite a lot of. Oh, yeah.
I received an email from a colleague from the industry, and it goes along lines which are already there, but basically he would like to. So basically, they would be interested in being able to have their tool chain in the cloud and be able to plug services. So more like assemble services and eventually have like commercial services with standard software that they use and they have validated, and maybe at some point do something fancy, or by fancy I mean like some processing that is not available in the commercial software, but which is available from, let's say, some research software, and which would be plugged into the chain. So it's a bit like what I said in the WP4 overview. So you have automated, capable, integrable, and scalable. So the integration part, that is, you can really assemble complex tool chain, but as services, and you can compose them.
Okay.
I would be interested in that.
Yeah. So I mean, I think generally we've had some consensus on a few things, but I think there's also some potential conflicts coming out. So one is what we were saying there, that there is a need to let the HPC guys get on with doing the HPC. And find a way to let people use it without them having to be experts and to keep up with all the trends that's going on in the HPC. And that's clearly a benefit that can be provided. And yet at the same time we said about the importance of making sure that people in other disciplines understand and how to use HPC and the value that it brings. So there may be some conflict there of, yes, we want them to understand how it works and to have some knowledge of it, but do we expect them to become experts in it? Or do we actually expect this to become separate? And again, that's potentially in conflict with what the Commission's saying in some respects. And the other was what you was just saying there, actually, that if we can get some building blocks, basically, that are efficient, composable, can be used, slot together and build something, then you do get away with taking away all of that complexity because they're already up and running. They're very easy to use. You don't need to know what's behind them, the whole black box issue. But at the same time, I get the feeling that a lot of the simulations require customization. And so this would only work commercially, I think, if the building blocks are generic enough to say, right, this is my product, I'm optimizing my product according to my mass market in inverted commas, so it doesn't have to be huge, but it has to be a set market. So I've got people from 6 different fields using this component, and this is what they need. I'm going to keep it simple and make a highly efficient, both in terms of cost, in terms of performance, in terms of ease of use component, which will be added to other bits, other building blocks, and then out of that they will build a bigger simulation. That can only work if you can optimize those building blocks. If every time you get a new customer you then got to go and modify them, that you start to lose a lot of the scalability and the efficiency of what can be done with the as-a-service model.
I don't necessarily agree with the genericity part. Actually, in specific software, it can be interesting because if it's linked to a particular tool or process, and if this is sold to some further clients, and you sell licenses to the. So, for example, I have a company who builds a machine that makes some measurements, and they use Fil++ for the processing of the measurements, and so they sell afterwards the machine with the software. But it's very specific. Then you sell the licenses. So
yeah, but if they
it's also interesting to have to understand how the market.
But if you linked that back and you said, actually, I'm putting it in the cloud, and this application will connect to the cloud and use the product that's running in the cloud, then you would have to customize the instances for this customer, or for their customers, in fact. So everyone who bought the machine would be logging onto, so they would have a customized version of it, and all of your clients would have. So you would actually end up with multiple instances, which are all multiple versions all running, and you wouldn't be able to get the economies of scale in terms of performance, in terms of. It's. I think it depends on the numbers, right? Ultimately. Okay. Any other comments? No, I don't know what the time is, but I think we've got time.
It's 7.
It's 7, so I think it's time to call it a day. Thank you, everyone, for your time and your participation.
That's all then. We close the session today.
Important point is the running session tomorrow morning.
You want to announce it? Please give him the microphone.
This doesn't need to be recorded. No, not or are we going to record the running in the So we'll meet in the outside of this building tomorrow morning at 7 o'clock to do one lap through the island, through the Margarita Island. We'll have our first lap at 7 and the another lap at 7:30. So
just to clarify, 7 in the morning.
Yes, of course. There are a lot of people running at that time. So and but anyway, if you didn't bring your running shoes or you don't like to run fast anyway, you are welcome to come and walking or however you prefer, and to join us and talk about the project during the running.
About the running of a project.
Where more precisely will you meet
In the main entrance of this building, we can meet there at 7 for the first lap, and then at 7:30, because this running is around the island. It's very, very easy. It's completely flat, so you're welcome.
Okay.
Thank you.
Okay. Thank you.
No problem, but you can go by walk.
Came by bike.
So you go to the festival.